Okay. So, how would you like to start this? Does anyone have some questions that you would? Oh, okay. I stand confused. Probably I should first say what does the exam look like? Because I was saying this in the waning moments as people are filtering out of the room on Thursday rather, and some people heard it, some people did not. By and large, the exam is a longer one. So there's quite a few questions on it. Not overwhelmingly so, but within the realm of what people will have seen in some of my other classes, 394, 371. The marks are distributed amongst a wide variety of problems. So, as I've characterized for other classes, if you are feeling not so good coming out of the exam, the general feeling you'll have is probably less one of being bludgeoned by just a few questions, instead being death by 1,000 cuts. You know, it's like, okay, I missed that one. You know, probably did pretty badly on these other 10, etc. The exam has questions of many sorts on it, and it covers many topics. In terms of the types of questions on it, there are everything from very, very short true-false questions to questions that ask you to fill in words and sentences, to questions that ask for, you know, one or two sentences in response to something, to those that ask you to make an argument for something, to those that ask you to interpret a little bit of code, to those that actually ask you to write code. And those that ask for feedback on code, sort of your impressions and suggestions on code. Okay? The questions where you're being asked to write code involve nothing beyond what would be needed for a single method. I'm not asking you to, you know, create Conway's Game of Life.
Like nothing in class is basically just functions.
No.
Okay.
Single methods. And interpretation of code. Well, okay, I should be careful what I say about that one. Yeah, all the interpretation of code involves code that involves things in single methods or functions. Although there's some question about whether it should only be a single function, but I'll leave you to decide that. Okay, so there's not much in the way of writing large amounts of code. Okay, but you should know syntax for some basics that we taught in the class, including Scala, yes, and probably something about Java 8's syntax. I'm not going to ask you for the details of C's sort of typing rules, how to write out a pointer to an array of pointers to functions or something like that. I'm not going to be doing that. But Scala and Java 8, I'd anticipate you wanting to have some good sense of some of the core things we covered there, and to generally be fairly versatile in writing methods and functions and reading type notation and creating them in Scala. Okay, and some of the example questions I asked were kind of along those lines. I need you to know about different types of collections. Okay, so now I'm getting into topics. But those were sort of a high level of the types of questions, sort of questions that full gamut.
Excuse me.
Yeah,
Will you be doing any writing of aspect J?
good question. Great question. I will not ask you to, I don't know if I should be saying this.
But should you,
I would not ask you to write aspect J.
But we should know aspect J.
You should know and you should be able to, you know, if you see me declare a point cut in code that's shown to you, you should be able to parse what that is. And you should know about some of the things you can specify in a point cut. And but more importantly, you should know what a point cut is and how it relates to a join point and how it relates to advice. Those sort of core concepts with aspect J. But no, I'm not going to ask you to write an aspect in front of me. Normally I ask you to write a trait in front of me. Okay. But I want you to know what you can do with traits. Scala traits. Okay, so a lot of questions, and certainly some of them involve looking at code and looking at specifications and reasoning about them. Okay, not unlike the sample questions I gave you, not coincidentally. In terms of topics, the sample questions contained many of the topics, and the easiest way to sort of talk about the topics that might be on there would probably be to actually show a few slides from my slide deck, because this gives you some very high-level understanding of some of the things I consider most important. And it may not be exhaustive, but it's pretty, oh no, okay, I don't want to, okay. Here we go. Okay, exam. Yeah, I know you folks want me you'd like me to look at something else here, but but no. Okay. Here we go.
will this be posted up after, or?
This file, yeah,
Okay.
yeah, not the entire contents of that folder, but yeah, this file will be posted. So yeah, all this will be posted in the you know, unless there's some maybe catastrophe, this recording will be posted. Okay, so Scala and Java 8, I do expect you to be strong on some understanding of cross-language comparison, big picture ideas with aspects and aspect J, and some understanding of the pieces that make up an aspect J program. Safe subtopic of subclassing, let's talk more about in the I just want to make sure this is the very latest version of this and not okay, the fox has shown its tail. Give me a second here. Here's version 5. Yeah. Okay. Yeah, that looks better. Okay. It's been a while working on this. Just wondering where my fruits of my labor went. Okay, so aspects and aspect J. If you did some forensics, you might realize that there might be a significance of the differences between what I just showed you and what I showed you here. So you could mine those last few video minutes for some insights. Safe subtyping and subclassing, we'll talk about that. Abstraction by specification, so benefits of specification and sort of encapsulation. And then abstraction by parameterization, both classic type and type-based. So expect you to be able to write type parameterized methods in Scala. They're just so much more beautiful, or at least they're less ugly in Scala than they are in Java. And I'd like to be able to write them. Like in the sample question, I asked you to create a thing that takes in streams and streams of arbitrary types or what have you. It can be type parameterized. Performance trade-offs between languages. Functional program. Basic concepts, closures, currying. One of the sample questions I asked you, we asked you to create a curry operator. Basic operators, map, reduce, filter, map values, those sort of things. Flat map, ladies and gentlemen, flat map. Performance and resource implications associated with pipeline style computations with streams or other constructs, and monads. Try, option, either, stream, etc. Futures, monads. Scala and Java 8 as important languages. Okay. So safe subtyping and subclassing, to expand on that, Liskov substitution principles. I expect you to be rock solid with this. Just really understand motivations for it, particular applications of it, the intuition behind why we care about these things. Reasoning is important. Subclassing concerns, separate from Liskov substitution principles, separate from the issue of subtyping or subclassing. Remember add all and add. Remember is positive, and if you override the getter and setter, do you also have to override is positive, or does it, because it makes use of the getter, you don't have to override it? There's a separate set of subclassing concerns that come into when you're implementing a subclass that are different from what's involved when you're simply reasoning about it. Is this a safe subtype in terms of the promises that it makes? And this subclassing concerns, this have to do with evolution of classes. Classes evolve over time, superclasses evolve over time, subclasses evolve over time. And how do you avoid one breaking the other? It goes beyond just what promises they make to people who use instances, and has to do with promises that we make to, for example, to those who want to subclass our class. So safe subtyping and subclassing, the use of specifications, preconditions, postconditions, invariants, history properties to guarantee that. Interfaces and classes, kind of trade-offs between this. We saw skeletal implementations related to this, wrappers and mix-ins. One way we saw that we could do mix-ins, have mix-in-like implementation was in fact with skeletal implementations and wrappers. Another way in which we can accomplish it is via traits. But the idea of a mix-in is important. Metalinguistic abstraction, the fact we pick our languages for areas of our program where they're most appropriate. So core areas of the program we might write in one set of languages, areas that need to be parallelized in another language, areas that just glue other pieces together in a third. We talked about mutability and immutability, value objects, the impact of mutability and immutability on reasoning and sharing and memory allocation, the fact that with immutable data structures, we could actually share them more readily. We can't modify them, so if we want to change, we want to insert an element into it, we have to create sort of a new formal dictionary, but it can make use of the pieces of the old dictionary because they won't be changing. So memory allocation, mutability, immutability, it's a bit of a complex balance where immutability forces us to create new instances of a data structure, but those new instances can share a lot of pieces of the old ones. Mixing of mutable and immutable objects, if you want to build up a thing out of these pieces that are mutable or immutable, what are the trade-offs? And then there's some links to the Liskov substitution principle. There's some gotchas with the Liskov substitution principle. You know, if you see a class that is read-only, it's clear, you know, from its specifications, from the definition of its methods as described by what they do, or if there's none of that, then what you would think reasonably by their names. If you could reasonably suppose that a superclass is immutable, there's no set methods, all it is a bunch of observers after you create instances, from then on it's not changed. If you create a subclass that is mutable, that is changeable, that can be changed, you know, like set the value of an element in a vector or what have you in space, then you're unless you've explicitly given the warning that this might occur within the superclass, you're violating the Liskov substitution principle there. That's a violation of the Liskov substitution principle. If the superclass is suggesting that it's mutable, and then you can have a mutable subclass. So if the superclass is reasonably assumed to be immutable, and you have a mutable subclass, it's just asking for trouble. Yeah.
Can you just do everything final?
Yes, you could, to prevent that, absolutely. So there's ways of preventing it. You could declare a final class, prevent subclassing at all, or you could declare, well, okay, let's be careful about that. You could declare the class is final to avoid subclassing. If you declare the methods in a way that they can't be overridden, someone could still create a new method called setX, which changes it. If you're talking about setting the fields as final, that would prevent those from being updated in the subclass. That's right. But you know, if I give you a problem where there's an immutable superclass and there's a mutable subclass, unless the superclass explicitly says do not assume immutability at subclasses, that's right away, it's a violation of a history property. That if you compare the value at one time and another time, they have to be the same, which is a property we might be counting on in the superclass. Okay, so these are important areas. Those are pretty good descriptions of important areas that I might ask about. Areas of the exam. There are some things that you don't see there. Do you want to ask about them? Yeah.
So I was looking at options, and I realized that an option can only be none if the value inside is a null. So what's the point of using options when you can always check if something is null?
Sorry. An option.
The functions that you pass the option into will automatically know if it's null and just not be.
Yeah.
It saves you from writing if statements all the time.
That is the key issue.
Another big thing is
So
that if
that's-
it fails like partly through, it will just simply stop and not waste computation.
Yeah, it'll actually short circuit it. It won't actually bother doing operations, but it won't break the pipeline. So let's say Val. Let's go write some Scala code. You folks don't look as excited as I am. Okay. Right? So here's option one, right? Sum of 3. Oh my gosh. Sorry, don't write that code. Hey, get me out of here. Okay. There we are. Okay. Now, we could here do something like val. well, we can create a none in several ways. One thing is we can actually create it from a reference that may be null and turn it into an option. We could also do, I think you should be able to do here, option of int like this equals none. Yeah. Now this is the deal, Tushita. I'm going to create a val null value. Okay. I'll call it v1, and this is going to be null. Okay. I'm going to say this is an int. Can I do this? No, it's not it's a mumble. Okay, fine. So this will be a string. Boom. If I try to do something like this, what do you think will happen? A bad thing happens. In case you can't see it. There we go. Bad. Right? It threw an exception. That's not good. Now, the bad thing here is that, yeah, let's do this. I'm just refining my example just so it'll be more compelling. Let's do foo here. So here we're going to have an option wrapping a string, okay? There we go, and we're going to have O2 be, I'm just sort of redefining these to be involving string. Here we go. None, okay? Boom, okay. So here we have two option values, option of strings. And you're saying, well, what's the difference between having a null versus having a none? There's a huge difference, because with a none, what you can do here is you could do, for example, map, right? Where I take, let's do this first for O1, then we'll do it with O2, where I take this and I concatenate it with bar, right? What happens if we do that with our O2? Remember what O2 is. O2 is none, right? So this is when we did it with O1. What happens if we do that with O2?
Still none.
We'll get back a none there. What happens if we do that with V1, which is null? What if we try to concatenate it with bar? Do you think a good thing? Oh my gosh.
It's literally the string
What
null.
the heck?
It
Okay.
said it equals null, and I casted it to the word null.
That's actually kind of scary.
We said it equals null, so it equaled NULL.
What the?
Clearly, null seems to be a type in and of itself in this. It will not let you assign it to things because it doesn't want you doing that.
Mumble.
Null has a two-string method. Wow.
Null can't have a two-string method. It doesn't exist.
Okay, this isn't what I expected, but let's take it. Okay, so suppose I say v1.toString. Okay, bad thing happened. So I see. Okay, so this actually is no. It's actually the value null. If I try to do, going back to my okay, that's really funky.
Null plus bar is null bar.
Okay. Moving right along here. Here we go. We're going to create a separate class. I'm puzzled by that, but I don't have time to sort of frog it. Okay, here's a class person with an age. Okay, we're going to create a. I'll create V2. Okay, here's a person, right? Person of 25, and here we're going to create, by contrast, something where we have a null person, right? So we're going to have a V3, which is null. Oh, sorry, which is a person. And we're going to assign that to be null. Okay, so here we are. Here we have a null value, okay? And if I ask for example, for V2, I ask for the person's age. We get that through a method that's built in. If we ask for V3.age, what do we get? we get something bad, right? This is a null value. Okay, now, what's the difference between nulls and sort of nones in terms of their processing? Well, the difference is that we can process in pipelines very easily without breaking it with a none, but we can't do that well with a null. So if we were to try to, for example, and let's try that here with a right. So suppose we were to try this. So here we have something that's null, and if we were to have a thing where we asked for the age of this person, we'd get back a null value. By contrast, if we were to have an option here, so here I'm going to have an option of person, okay? It may or may not hold a person, and it's going to be sum of person of 25, okay? And this other one, 04, is going to be none. Here we are, none, right? So we have 03 and 04. Here I could, for example, say dot map, and I could map this to their age, right? And you'll notice what happens. This is an option going in, and I map them to their age, and I get an option coming out, right? Map on an option returns an option, right? Okay, now what happens if I do that for 04 here? What if I try to perform that with 04? 04 is a none already, and I try to map it. I try to apply something to extract their age. I get back a none. Okay? It's actually recognizing that this is something that is none, and anything that tries to access something within it by extension is none. Meanwhile, if I try to do that, if I try to extract that value directly from something which is null, I'll get back something which yields an exception. Okay. Here, I basically have to test, okay, is this thing null? Then, if so, I'll treat their age as null. This is a contrived example with very simple cases, but where it gets particularly important is if you had something like, imagine if you were interested in asking about this person's, so we have a person, and we want to find from them their first child, and we want to find out, if that child's, we want to get from that, so this would be a child relationship, and we want to get from that, their own first child, or something like that. The issue here is that, so child of 0. The issue here is that, first of all, we may not even have a reference to a person, in which case it's none, and this whole thing should return none. Alternatively, we may have a reference to a person who doesn't have a first child, in which case asking for their first child should return none. Alternatively, we may have someone who does have a first child, but they don't have a first child, in which case it can yield none for that. Now, could we do this with null by reasoning about null? Yeah, we could. We could say, well, if this value is null, then we will simply treat the results of the whole thing as null. If their first child is null, or they have no children, we will treat them as having a null return as well. And if that child's first child is also 0, we will treat it as having a null there. But it involves a lot of checking along the way. Basically, each step along the way, you've got to figure out, do I have a legit situation? If not, return null. Whereas that can automatically be done. In fact, one is tempted to say automatically it can be done here with options. Basically, it short circuits that process, which allows you to have a long pipeline of successive operations, which is modular, which is easily composable, which can allow you to sort of swap out components or put them in, and which is readily understandable and in fact can be performed incrementally with lazy structures. And basically, if something comes up along the way that's an invalid value, instead of breaking everything down there because you can't call it on a null, it simply returns none, and from then on there, it's nulls, it's none all the way down. Every successive step is just applied to none, and you're going to get back a none, as a result. So in short, when you have multiple steps involved, rather than just one step here, this ends up being a lot less cumbersome than with null. And this is a sort of trivial example of a multi-step operation itself, but often we'll have pipelines that are 10 things long, and being able to handle an error at any point along the way without needing to bomb out of it by an exception or bomb out of it by checking, oh, it's null, so we can't continue. It's a real advantage. So with these, we could just continue performing it all the way through. And I should say that I believe in Scala, there's also a way to, is it from nullable or of nullable? There's a way to very easily turn a null value into an option. So you can basically, if you have a null value, you can turn it into an option value trivially as a none. And from then on, you can apply operations to it without worrying that they're going to blow up in your face. They will return none. Yes?
So is it true to say that none, so options are only useful in pipelining?
In pipelines?
Yeah.
No, although that's where they, like Saskatoon, they shine. Yeah, don't ponder that too deeply. It's not that Saskatoon has a deep link to pipelines. That would be more like Fort Mac. But okay. So, ladies and gentlemen, options in general are useful for encoding cases where we may or may not have a legitimate value. It is typically when we have a composition of a set of steps that it becomes most awkward to handle these exceptional cases where we don't have a legit value. Pipelines are a good example of that, but they're not the only example. There's a lot of cases where we don't want to have something that's of a totally different nature, like a null compared to a legit reference hanging around, because we have to special case it in our code. We have to put in place some mechanism that says, in this case, do this. And pipelines are one case of that, but there's a lot of cases where we're going to need to do processing, and it's just cleaner to be able to specify it as a value of the same class, option event, but where when we try to process it, it returns values in a kind of well-defined way, given the fact that its value is none, and therefore things applied to it, its value is none. So I'd say it's more than pipelines, but pipelines are where it shines. Okay? And some of you might even take a shine to it. Yeah?
Was there a purpose to making just that single class a case class? Because they give you an additional benefit if it's just that one variation of it?
Very good question. Why did I do a case class there? I did a case class because I wanted it to auto-magically provide me with goodness. And let me expand on that puzzling statement. So this is, I think, to what you refer. I defined it as a case class here. What does this give me? This is usable material. What do I get out of declaring this a case class? Yeah. A companion object is one thing I get. There's a companion object associated with this that has certain methods defined. What is that companion object good for? Companion objects they're kind of like, they can support singleton operations. Those of you intimately familiar with Java will know that if we want to create singletons in Java, something that only exists there's only one of it for the entire class, not for each instance of the class, but for the entire class. What do we use? We use static, right? And we can do that for a method, we can do it for a field. So we could have, a count that is meant to be the count of number of instances allocated of this class. And that count belongs to the whole class. It relates to the whole class. It's not each instance. We're asking how many instances have been allocated, and we declare it as a static field, a count. And we'd increment it every time we allocate a new one. Just like that. So in Java, we have these static things that we create to create singleton operations, or to insist there's only one instance of this class, for example. In Scala, you don't have that. There's not this static methods. What you have instead is a case class that has an. I should take that back. That is one way to do it. But to generalize it, what you want is a companion class. So there's a companion class, and that encapsulates all the class-specific, the class-related information and methods, etc. So this has, by virtue of declaring as a case class, as Tushita noted, this automatically creates a companion object. If you'd like to engage in fun with the REPL, you could do Java P here minus public, and the name of that case class is person $. And there it is. It stands before us. Okay? So I'm looking at the public methods of this case class, which were created automatically. And you notice that there's many good things in there, including an apply operator and an unapply operator. What does that unapply operator do? Yeah, it breaks it into its constituent parts. So, if I had, I'm trying to cover a lot of different things that are good things to cover for you here. If I had, something like this, case class person with age and income, then it's more, it's better suited. Unapply would take a person and break it into their age and their income, right? So I could do something like this. Val P1 equals person, age 22, income $25,000, something like that. Okay. Of course. There we are. There's the person, and then by virtue of doing that, I could do something like this: Val, person, age, comma, my age, my income, just to emphasize that it doesn't have to be the same name, equals P1, and it will destructure it. Do you see what happened? What happened here? What happened?
Assign the values of the instances, or the
Yeah.
fields into age and
Yeah,
income.
and through what method did it do it?
Unapply.
Through unapply. It performed unapply, ladies and gentlemen, on P1, and that returned some of a tuple, I believe, if memory serves me, so it returned. It's an option, so it returns it. Yep, tuple 2. See it? See it there? Returns some of a tuple, and what is that tuple holding?
The age and income.
The age and income. Yeah. So these things are defined automatically in the person class. That's one thing that's given in the person object, rather, the companion object associated with the person class. And here's the similar methods within the person class. So one reason I declare a case class is I would like to see the I would like to have a companion class automatically created and unapply and apply. What does apply give me in a companion class? What does that give me the ability to do? In fact, you saw me do it just a moment ago.
Create new objects without.
Yeah, without saying new person, right? This is actually calling apply on the person companion object. That's why it allows me to say person. If I had apply in the class person, what would that allow me to do?
Call instances if they're
Yeah, I could call instances if they as if they were a as if they were a function, foobar. You know, I could do that if I had apply defined in the class. But it's apply being defined in the companion object for person that allows me to do this rather than doing mumble. No, of course. Yeah, keep on making that dumb typing thing. Okay, I could do that, but it's much nicer to be able to do this, and that comes out of doing this a case class, having a companion object which has apply defined. Okay, but why else did I do it as a case class? Because it gave me something else in the main class. That's what I did it. I wanted to be able to have automatically a thing for extracting the age and extracting the income. And you'll notice that this gives me automatically those access or methods to get the age and the income. Okay. I wanted that so I could do .map, you know, where I extract the age without defining it manually. So it gives me these good things there behind the scenes. So that's another reason that I did that. Okay. Okay. So other questions?
Can we go over the sample questions?
Can.
And we will know what to expect.
Sure. Do you want me to go over the sample questions? Is that good?
Yep.
Okay. Okay. Let's do that here. Oh no, you don't want to see that. Well, you do. Okay. I got to be really careful here.
Why is that open? That's my question.
Literally unplugged like the H200.
Oh, okay. Sorry. Let me just. Here we go. Here we go. Okay. Oh. There we are. Okay. Okay.
Can we assume that this finals length is almost the same as this finals?
No.
No? It's longer?
The real final is longer.
Okay.
Like it would be a bit easier if it was only 2 questions, but
Yeah. It'll be easier to mark too, but
yeah.
I think that's not in the cards for either of us. Typically, it takes me 45 minutes to an hour to mark each final. So you may be in it for 3 hours. I'm going to be in it for something like 30 hours. And if that's any
30 hours, it's going to go again and again and again and again.
Yeah. Okay, so here we have a bunch of little examples here. Is find timer a behavioral subtype of course timer?
Somebody can kind of, can you page preview? That should get rid of some of the more stuff so you can see more of the actual.
Oh, okay. Or I could probably just, this sort of thing.
It's the
Like
toolbars.
it's like the top 3 lines of junk on the HUD doesn't really do anything.
Oh, you mean this junk?
Yeah.
Okay.
Page preview or something.
Sure. Page preview. Okay.
That didn't help. Versus-
You just click on the down arrow there and say-
Here. Well, mumble.
The one beside close preview might be full screen.
Yeah, it is.
This guy.
Yeah.
Okay.
Yeah.
Okay. Now we're talking. Okay. Course timer and find timer.
Yes.
I'm glad I'm not live streaming this. Okay. So.
Did you resume the recording?
Yes, I did resume it. Yeah.
Yeah.
Yep. I've resumed it when we're in a safe place. Yeah. Yeah. Okay. So, ladies and gentlemen, is find timer a legitimate subtype of course timer?
Yep.
Yep.
So, what things to look for here? Well, one thing to look for is, does it override any functionality of the supertype? Is there any method that it overrides?
No.
No. Does it change the supertype in some notable way in terms of invariance and history properties? Like, is the supertype read-only and the subtype not read-only?
No.
It still starts it the same way, it still can't stop.
Yep. Here, find timer provides some additional functionality. It reports seconds. But if you were dealing with a course timer, would that affect you at all?
No.
No, it's something which reports on some additional information. If you think it's a course timer and it's secretly a find timer, you're never even going to call seconds. And if someone else in the code base does call seconds, it doesn't affect the behavior up here at all. It's just an observer down here. Ladies and gentlemen, those are, well, I'm not going to say that those are bulletproof demonstrations. They're hallmarks of the fact there's nothing wrong with this in terms of the Liskov substitution principle. You have this subtype which provides more information, doesn't interfere with by either overriding or by changing the behavior of anything that's visible with the supertype. So if you had a course type, could you be rudely surprised if somewhere in the code, if what it really is a find timer and someone else in the code knows that and is doing things with it? No. Doesn't change the behavior of this at all. So it's a perfectly legitimate subtype. Okay. Okay, so is modulo timer, this one down here, is that, maybe I'll blow it up one more level yet. Let's I'm now attempting fate a little bit. Maybe optimal view, mumble. I think I'll just keep it at the same one. Okay, here we are. There we are. And there we go. Okay. Modular timer. Okay. So is this one a legitimate behavioral subtype of course timer?
Nope.
No.
Why not?
You can't hit 60, and you're supposed to be able to.
No, it's that the minutes is completely flawed.
Yeah,
If we do
that's
minutes
what I
of
said.
course timer, we'd have, say it went for 2 hours, we'd get 120 from the course timer, we
Right.
would get 0 from the
Right.
modular.
Okay, so a couple things to look at here. So good. Both you and Connor, I think we're grabbing onto the one of the correct answers to this. So the first thing is minutes is overridden. That should draw your attention immediately. We've overridden minutes, so we should be looking to see if minutes is consistent in terms of its basic properties with minutes in the supertype. Now, the basic properties associated with a method that we look for the Liskov substitution principle are what? Are,
History properties and invariance.
okay, that's for the behavior of a class collectively as influenced by many different methods, like can it ever go down and that sort of thing. So that is one thing, but on a method by method basis, what you're looking for a particular method, you're looking for preconditions and postconditions. So I would ask you, are the preconditions associated with this method the same?
Yep.
Yeah, there's no change of preconditions. Are the postconditions the same? No. The return value means something different. I mean, the mathematical function captured by the subtype, a modular timer, that it returns, as a function of the time since it was created, is very different mathematical function here. It's almost as if we overrode square root in the supertype to be something that's called the same thing but returns the cube root in the subtype. It's different. I mean, it's mathematically different. We're doing something different. We're returning something that in fact is a different function from that in a mathematical sense, the result of applying a different function. So the postcondition is off. That immediately tells you that no, this violates the history properties, because what can we do can we have, let me ask, let's sharpen this a little bit. Can we have in a subtype, something which differs in its postcondition? So method A in supertype, method A also in the subtype overridden with a different postcondition.
Yeah.
Yes? In what way can it differ?
Less strict return, right?
More strict.
No,
Oh,
more strict.
More strict. Anything that is returned by the subtype must be something that can be returned by the supertype legitimately. So the subtype might, for example, with square root, it might guarantee a more precise value, even closer within some even finer tolerance to the true value of the square root. And the supertype just guarantees it at a very crude, level of tolerance, a very crude level of accuracy, where the subtype is very, very accurate. That would be perfectly legitimate. What wouldn't be legitimate is if the subtype loosens it. The subtype can return something that's up to 1 different from the square root, the actual square root. That would not be legitimate. So the subtype for postconditions, and the thing that's a little bit confusing here, it's different for preconditions, postconditions. For postconditions, the subtype can only what? Strengthen them. They can only be they can either be the same or more specific. It's like this, ladies and gentlemen. Do you remember Fred X?
Yes.
Yeah, maybe you wish you never met him, but Fred X, if you brought your package to Fred X and you said, wow, it's from the FedEx website, it's a 12 p.m. deadline, and I'm walking in at 11:58 with my form all ready to go. Here, Fred X is my package. Get it to Toronto tomorrow by 5 p.m. And if they were to tell you, no worries, we'll get it to Toronto by midnight tonight, would you have reason to be upset? Not in the least. After all, what they are telling you is different from FedEx's website, but it's different in a way that's still compatible with it. It's more specific. It's within the bounds of what FedEx promised, but it's a subset of those conditions in a way that would be suitable. Let me ask you this. Suppose they told you, we'll get that package to you, indeed, by 5 p.m. tomorrow, but we have to let you know it's going to get there between 4 and 5 tomorrow, with complete assurance. We're going to guarantee it. It's going to be there with complete certainty by 5 p.m. tomorrow, but it will be between 4 and 5. Could you be upset then? No, it's within the realm of what FedEx promises, and so you say, well, okay, well, good to know. That's the way it is. It's compatible with what FedEx promises. But if FedEx told you, okay, actually, it's not going to be there by 5 p.m. tomorrow. It's going to be there by midnight tomorrow. Would you have reason to be very concerned? Would you have reason to object? Yes, absolutely. So, ladies and gentlemen, the subtype FredX can only be the same or more specific in terms of the post conditions when the package gets there. How about for preconditions for a method in the subtype?
Supersets.
Yeah, it could be superset. It could be a proper superset, or it could be the same. So here, what's the analogy with FredX?
You can bring it in later.
You can bring it in later. You're pleasant surprised. You're sweating bullets because you got it there at 11:58, and then you realize that your watch is running slow. You walk in, they say, "Oh, don't worry. Here at FredX, we use advanced logistics algorithms to allow you to deliver it by up to 2 p.m. and we'll still get it there." And you say, "Okay, that's great. It's a weekend precondition. There's no way you'd be objecting because they provide all the guarantees. If you get it there by noon, it still gets to Toronto tomorrow by 5 p.m. But they handle a larger set of cases. So the preconditions and postconditions for the subtype don't have to be the same, but they have to be compatible. And these ones are totally incompatible. The postcondition for minutes in the subtype is is incompatible with the post condition for the subtype for minutes in the supertype. It is mathematically not the same function. It's it doesn't yield the same values for the same set of preconditions. So on that point, it is invalid. But there's another argument you could make about why this doesn't match Liskov substitution principle that doesn't involve directly preconditions, postconditions. What's the other argument? It violates a what?
History property.
Does violate a history property. What's the history property?
Minutes can't go down.
Minutes can't go down in the supertype. You could be counting the minutes. There's no way the minutes could be going down over time at any point, but it is going down in the subtype. So from either the history property side or the... So remember, invariants have to do with things that can be checked at any one moment, whereas history properties are things that are checked between 2 points in time. Time A, time B. Yeah?
Can you give like another, for all the examples we did in class, they always violated the history property over and over again. We never really went into invariants being violated. We kind of talked about them, but never showed an example.
Sure. So an invariant being violated would be something like a counter. A counter. So maybe your counter is defined in the supertype to start at 0. And from an invariance perspective, it can only stay the same or go up. But more to the point, from a perspective of, from a history property side, it stays the same or goes up. From an invariant side, it's always 0 or more. At any one time, it should be 0 or more. Now imagine you defined a subtype that allowed that value for the subtype to start at negative values. There, it would be objectionable because by the declaration of the supertype, with this counter, you can never have a negative value. At any one time, it should always be 0 or more. It's the original value or it's been counted up. Whereas this subtype, you could start it at a negative value. Or you have a subtype that can decrement it. Yes, that would violate a history property also, but it could also violate an invariant in the sense that at any one point, you might see a counter that's negative.
That was the part that confused me. It could violate both, I see.
It can violate both. There, it would violate both with the criteria being a little bit different. It'd be objectionable as a violation of an invariant because it's negative. You could check it and it would be negative. And you'd say from the supertype, it can't be negative. It always starts at 0, and it can only be more than 0 at any one time. It's objectionable from the standpoint of a history property in the sense that it
goes down.
It goes down, or it can decline rather than simply staying the same or rising.
So it violates the history property the first time you use it, and only the invariant to actually use it a few times, probably. Once you finally get past 0.
Yeah, I mean, you could immediately decrement it, and it would immediately violate the history property and the invariant in the next observed value. But yeah, that would be a violation of both. Warren, I saw you first and then sheet.
Yeah, I mean, an easy example of invariant violation would be like, you always expect the length and log it to be positive, right?
Yeah.
You would be very surprised if it gave you a negative all of a sudden.
That's exactly right.
Some fun for loops when that happens.
And what you're referring to there relates in a way to a couple other examples of invariants I've mentioned in passing. Another invariant you could check at any one time in your data structures invariants are really easy to check with assertions. There are things like, does my hash table have any keys that are null? Does it have any values referred to by keys that are null? Are any of the strings in my vector of strings, of 0 length? Are any of them null in that vector? These are all things that would be aspects of invariance, and at any one time you could check, does this data structure match this invariant? Does it adhere to this invariant? And a lot of the times we are counting on those invariants in our code. We're counting the fact that, I never, ever, ever insert a null thing into this map So this dictionary, so when I look up a key, I should always get something that's not null. And a violation would, that might be something that's in a supertype, and a subtype might violate that by allowing insertion of nulls, and then bad things can happen, because your code up there, which was written in a way that said nulls never happen, so we don't even have to check with them, breaks. Are those helpful comments? Yeah. Okay, Tushita.
Good.
Yeah.
Can there be a case when the invariant, you can, can there be a case when you do not have the invariant working, but you have the history property working?
Yeah. We could imagine a counter that allows for initialization at any integer value, and but it only provides an increment operation. And now imagine a subtype of it that further provides a decrement operation. There's any possible value of that counter involving possible values of integers could have been produced by creating it through the constructor with different values, negative, positive. So there's no issue of an invariant breaking, but the history property can be broken there because it can go down. And you would think from the original class, whatever number you created to start, it can only stay the same or go up. But now this subtype could have it actually going down. And someone says, wait a minute, this is the same counter I've been dealing with. I've been incrementing it over time, and now it's declined. There's no way this thing can decline. It's because somewhere else in the code it knows it's a flexible counter, and it's called decrement on it many times. And someone can be rudely surprised because they've written the code, they've structured the code around the assumption that this counter can only stay the same or rise. Like they're using it to successively write values of into indices in an array, and at the end they'll stop. And now it's declining, and the algorithm may never finish or something. So.
Yeah. Sorry, my question was the other way.
Oh.
So.
Could it?
So when you're violating an invariant and not violating an history property.
Violating an invariant, but not a history property. Length.
Length doesn't usually change after you've created something like a string. Strings are usually
Are usually immutable, but they could be of zero length. So maybe you have a case where you have, I'll review with you just a second, where you have an array, and you are within this, it could be zero length strings or it could be null things. If you're counting on this array holding, so again, you're saying cases where an invariant is fails even though the history property does not fail. So sure, an array of references to strings where you're counting on them being all references to legitimate strings, and instead you have a null in there because you've assumed in the super type there's no way you can have an inserted null. You're just going through the array and calling each of their lengths, getting the length of each one by calling length on it, and suddenly in the subtype someone says, for my array it's more flexible, I can put nulls into it, and now your code written with an understanding of supertype guarantees will fail, but there's no real history property that's been violated there. You haven't changed something in a way that seems impossible in terms of its behavior over time. Okay. I think. Okay. Well. Okay. Because you could say, okay, a derivative property is you can.
Imagine a subclass of string that where length could be -1.
Yeah. Yeah.
What about a subclass of timer where you start at -5 instead of 0? For the first 5 minutes, you're going to be the first guy you're going to go.
Because you're still going up. That's still the rule.
So the history property there would be observed,
Yeah.
but the invariant will be violated.
Yeah.
Yeah. Good. Good. I like it.
Because it
I like
being
it.
at 0 isn't part of the history property.
That's right. That's right. It starts negative, and there's no there's no issue that it's time 1, time 2, where time 2 is later than time 1. It's changed. It's an invariant. At any one time, it can never be negative. It has to be 0 or more. There's no issue that it's changed over time in an adverse way. Good. I like this discussion. Other questions about that? Okay, let's go on to the third one. So is pausable timer a plausible timer? No. Is pausable timer, is that a legitimate subtype?
Because you can't get the same time twice. That's a rule. If you waited a minute on a pausable timer, you could get the same minute.
But that's allowed.
No. In the superclass, you can't have a minute long return the same minute twice.
Well, it breaks the assumption that the time is from
The
when it was
elapsed time,
created.
total elapsed time.
If you pause it, that's no longer true.
Yeah. Okay, this one is actually somewhat subtle. Is there an invariant violated here?
It's constantly increasing, that's the kind of rate you expect.
Okay,
over time.
but the very notion of increasing means it's changing from time 1 to some time 2. It's
Like,
rising.
Consistently though, is the big thing, is that will always,
Okay, but
I mean, with the incrementary, you don't have to expect that, but with the timer that keeps increasing over time.
fair enough. But that's an invariant is something that can be checked at any one time. Like, are there nulls in this data structure? Are there null values, or the null keys, or null
If
elements?
it's anything that involves happen, it's a history property.
Yeah, exactly. If it happens over time, and here so is there a different precondition associated with any of the methods that have been overridden? Are there any methods overridden? No. Is there a difference in postcondition?
Yeah.
Yes. There is a difference in postcondition associated with what's going on.
It's no longer the time since creation.
This is correct. It's no longer the time since created. It is, again, mathematically it's something else. Now the interesting thing is here about that is that we actually haven't overridden minutes.
We've overridden the behavior of the underlying whatever's ticking that we can't see.
Yeah. Yeah. We've overridden the meaning of minutes by presumably we're frobbing some underlying variables that are keeping track of, when was it, well, we're introducing variables, when was it paused. We would probably have to plausibly,
There's more functions that would probably need to be changed for minutes.
either we'd have to awkwardly write to the time it was created and pretend it was later, or we'd probably have to override minutes. But maybe minutes is using some sort of calculation that is based on some data structures that we're changing. The point is we're changing the meaning of what this performs, and that's not a legitimate subtype. It's not. Could someone be? This is the question. Could there be properties someone is counting on with course timer that are violated by plausible timer?
Yeah.
Yeah. They could be counting on a property like the fact that it gives you the time since it was created, and suddenly they're saying, wait, that's impossible. I've given this thing 5 more hours. It's still saying it's only 2 minutes since it was created. So someone could reasonably be counting on properties associated with course timer that are violated, in fact, by plausible timer. And that's really the question. Are there properties associated with a supertype that are being undercut or being violated by the subtype? Are there properties that someone could be reasonably counting on, seeing only the definition of the supertype, that are being violated by the subtype? Okay, so next one down. Is resettable timer a subtype?
Just with the name, no.
Yeah. So what does this violate?
History properties can't go down.
Yeah, so it violates a history property. Violates a history property. Does the previous one violate a history property?
Nope.
Not really. Possible timer didn't really violate a history property.
You can have two the same minutes over time. They're
Yeah,
just
exactly.
hidden seconds.
Yeah, it could, and I think that was the point that was being made earlier, that minutes, for any two observations, minutes could be the same. It's just that the semantics of what minutes meant was different. Now with resettable timer, you're actually violating the history property. It can be, previously, the main class, course timer, can only be the same or rise, and suddenly here it can go down with resettable timer. Okay. Okay. So okay. So is fine. Compare, contrast, explain the benefits and shortcomings of using a wrapper class versus subclassing.
We just had an interface instead. A timer interface would have been the best way to do all of these.
Okay, but in the actual exam, I would set this off to be a different section or clearly different. This question is actually unrelated to the previous ones, or not directly related. So it's just asking wrapper classes versus subclassing. What are the trade-offs there? Give me a advantage of wrapper classes that you don't have with subclassing. What is a wrapper class?
It's a new class that contains the old one inside.
Yeah, okay, and if you call a method on this new class, what does it do?
Probably calls one on the inside.
It probably calls one on the inside, although it might do some additional things, right? It might keep track of some extra information, like the number of ads that have been performed, keep track of extra information regarding, or append information to what's returned or what have you. So what would be one advantage of doing that rather than subclassing?
You don't risk violating the list-off substitution principle.
Good.
Because it's not a subtype.
It's not a subtype, so you don't risk violating the list-off substitution principle.
Another one is encapsulation. The end developer doesn't have to worry exactly how timer works. All you have to care about is the wrapper.
Yeah, ladies and gentlemen, this is a very important point. And it can be valuable for the exam too. Ladies and gentlemen, there's a very different relationship you have. If you consider class A, which has some methods in it, let me be fair to the side of the question. If you have some class A with some methods in it, and I'll use an example from class, add and add all. Or maybe these are, instead of add and all, I'll give another possibility. It's, get value, or get and is positive, or something like that. If you have a class A, and you're using an instance of that class A here, a new A, and you're calling these methods, you're calling add all or what have you, add all, or you're calling, is positive or what have you. Your relationship to that class, what you care about that class is different and is simpler than if you were in fact subclassing class A in a separate class, class C. Why is that?
You're just a user.
You're just a user of the class. And you don't care internally, for example, does add all call add? Do you care? No, as long as it does its job, as long as it adheres to its promises, you don't care whether add all calls add or not, right?
Because you don't create add anymore.
Yeah, you're not overriding add. And that's the rub. When you're dealing with a subclass and you are overriding add, you now do care very much, does add all call it or not? for certain types of needs. And I gave an example of class where you're counting the number of things inserted into a class. You care a lot. It's an add all call add. So when you're dealing with a class simply using an instance of the class, you care about instance specifications. Specifications to say what each method does, maybe what the invariance and history properties are. When you're creating a subclass of this class, you actually care about aspects of the implementation, and you care about an inheritance interface. An interface that provides additional information. And the two that I talked about were you care what calls what, and you care like what things have to be overridden together. So if I override get, I might, of necessity, have to override set with it, because otherwise setting is setting one thing and getting is getting something else. So I might have to override certain things together at the same time. So ladies and gentlemen, when you're using a wrapper class, how are you interfacing to the thing that you're wrapping up? So if we want to compare subclass in class A versus creating a wrapper class that wraps up class A, what are the relationships needed of each? For a wrapper class, what are we dealing with class A? As if it's
The public API.
yeah, we're just dealing with the public API like we're dealing with an instance of class A. We're just using an instance of it internally and calling off to it. So we don't care about whether add all calls add. You see that? You don't care whether add all calls add or not. It doesn't matter to you. And you don't care in the future if it changes to call add or not. That's up to it. As long as it adheres to its specifications as indicated by the interface, you are fine in a wrapper class. With a subclass, is that the case?
No.
No, with a subclass, you're actually overriding things, and you sure as heck care does it in fact call it, and you care about how it evolves, and therefore you need extra set of promises through an inheritance interface that says, from now on, can I count on add all calling add or not? So subclassing tangles you up. And if you're creating a subclass of a class A, your class is tangled up with the future of that class A. It's getting entwined with it. And meanwhile, a wrapper class steps back from it. But what's a shortcoming of a wrapper class?
You have to re-implement everything.
Yeah, you have to go through and tediously sort of re-implement, do this delegation stuff, etc. It's tedious. It's somewhat ugly. It's a lot of boilerplate, and it's very easy to look at it and miss the essential logic. Ladies and gentlemen, when it comes to code, one of the things that troubles me, I remember one time the department head came outside my door. He was sort of hanging around outside visiting faculty and just happened to look in at me while I happened to be looking at some student code from 371. And he saw me leap to my feet. And he wondered what's going on because I looked shocked and dismayed. And I showed him this code. I said, can you believe this? Have they no sense of dignity? I mean, ladies and gentlemen, sometimes you look at code and it's pasted again. This was not this semester.
This was long ago. This is an old story.
This is an old story. Yeah, don't worry. This is not ID5 for sure. No, it wasn't this semester. It was a long time ago. Not in a galaxy far, far away, but with a different department head. Soon, 2 department heads ago. Anyway, there's a lot of time, ladies and gentlemen, that when you look at code, there's just a lot of cruft there. There's just a lot of unnecessary detail that gets in the way of understanding. It gets in the way of appreciating what's the essential thing being done. What's the heart of this code? What's the most key logic in here? It gets obscured by a lot of boilerplate. gets obscured by a lot of just pro forma stuff. And there's big dangers to that, because often you're trying to get to the essence of it, and you're just set off by all this, things that are full of sound and fury but signify nothing of significance. Shakespeare wasn't talking about that in his play, but he could have been. There's a lot of code out there that's full of sound and fury, but signifies nothing of significance. And an unhealthy amount of it is produced by CS students still in training. No, this is not to cast aspersions, but you'll have to learn to cut through it. And much of what I've tried to teach you this term has been in providing linguistic choices and ways of phrasing things that try to cut through it. Like this whole nonsense with checking for nulls at each level. Is this null? Is that null? Is that null? Operate with options, ladies and gentlemen. You save yourself so much time. Combine them with for notation in Scala, and you can just have code that's beautiful because it gets down to the essential operations, but it handles all the error conditions as well. End rant. But popping off the stack, with wrapper classes, we have a lot of cruft that gets in the way of noticing where the essential places are. It's changing things. So those are some differences associated with wrapper classes and subclassing. Okay, contrast between types of information included within the specifications commonly provided for a class's instances versus those required for subclassing a class. Okay. What calls what is one thing. What things have to be overridden together? Because sometimes there are chunks of functionality that go together. They all use the same instance variables, and if you're going to change those instance variables, you gotta override them together. If I were to change it so that it wasn't using an array but a bit vector, I've got to change the set of things together, these methods and these data structures together. It's kind of chunks of functionality that sometimes have to be overridden together. And that, for example, again, set and get. Okay. Assume that we're considering subclassing a class and happen to have access to the code for that superclass at the current time. Describe three distinct difficulties that can arise when hoping to always just rely on studying the code of this class to decide how methods of the class will perform when used by our code both now and in the future. Okay, that's poorly worded. Okay, so the question is, why can't we just peek at the code? So, I've had students tell me, hey, if this is an open source system, then let's go with substitution principle. We don't have to worry about it at all. Or we don't have to worry about subclassing, because we have access to the superclass. Why does that break down? What's that?
Famous last words.
Yeah, right. Why does that break down?
Because it changes, people make better code.
Yeah, it changes. Whether in the superclass, people maybe before were calling things in these ways, and now they've changed it, and you're counting on this code, relying remaining the same in terms of these properties. So that can lead you to break your subclass code. There are also cases where your subclass code can break the functionality of the superclass. Because you've overridden this, people in the superclass are counting on certain types of behavior in the subclass that your class doesn't guarantee, and maybe that changes over time, and you end up finding that your class breaks future versions of the superclass.
Their post conditions change and yours stay the same.
Right. Yes, their post conditions might change.
So wouldn't that break?
For example, they might now put in place a an implementation of square root that's more accurate, more precise, and yours doesn't stay the same. And
Perhaps
now,
theirs gets faster and yours has, it assumes that it has a better guarantee now, but they're still using your old subclass secretly, and so your performance is crap in comparison.
yeah, so that could be. So in other words, they provide certain performance guarantees which your class doesn't adhere to. So if someone's using an instance of your class, those performance guarantees might not stay those.
And when you made that class, you were fine, but they made it better.
Right. Okay, so that's good. Okay, so fundamentally, the evolution of the superclass can break the subclass, or it can be broken by the subclass in those ways. And a third distinct difficulty would be if, it's cognitive burden to have to go look at this code base and check it to know, is this safe or not? Now we have to get entangled with how is that implemented and is it safe? It's nice if we could just have a statement about what's guaranteed and live by that. Guaranteed now, guaranteed forever. Okay, given two infinite length streams, stream A and stream B of type stream T, write a method in Scala that produces a stream whose successive elements are drawn from one of the streams, where the choice, okay, there's a typo here, choice of the element of the element to use for the next stream element is determined by a flip of the coin. So the idea here is we might have two streams. Maybe it's a stream here. I'll write it, I don't know, with double curlies or something. 1, 2, 3, 4, and maybe another one is 0, 1, 0, 1, etc., just alternating in that way. And so we want basically a method which is going to produce a new stream whose elements will be drawn successively from the corresponding elements of these two streams. Which one it used will be determined by a flip of the coin. So maybe it would end up being, by luck of the draw, the output would be something like 0, 2, 3, 1, etc. So this guy is from here, this gal is from here, this gal is from this one, and this one is, oops, this should be a 0. That should be a 0. Yeah. No, that should be 1. This one is from there. Yeah. Okay, so how would I do that?
Oh, so we're not, no, that's not right. We're supposed to be pulling out of the stream, not bits of the stream.
Sorry, we're taking
You
six.
can't skip from 1 to 2.
Can't skip from 1 to 2. The way it was intended is basically you're going to, for the first element, you're taking one of these first elements to the next. For the second element, you're taking one of these second elements for the next.
I thought it was a randomized flat mapping zip.
Right. Oh, that would be sweet, but no. Okay, so how do we define that, ladies and gentlemen? How do we do that? Tell me what to type.
Can we make a method, and then make a call to the stream that uses that method?
Good. So first of all, let's important Scala dot util dot random. What do you think? Yeah? Okay, here we go. And then let's do def random elements for two streams. Okay, how am I going to, this is going to be something that takes a stream of type T. How am I going to, can I just say, stream 1 is a stream of T? Can I say that?
Yeah, you have to define T.
Okay, where do I define T?
Think in square brackets right after the name.
Good, just like that. You folks should know how to do that. Okay? So this is going to be stream 1 and stream 2. Stream 1 and stream 2. Okay.
Stream 2.
Stream 2. Thank you. And what is it going to return? We don't have to tell, but we'll do that. Okay. So what is this going to be?
So you could do
Yeah. So okay, if
next Boolean,
Next-
whatever integer of stream 1 else
good.
integer stream 2.
Okay, next Boolean. Don't tell me next. Okay, next Boolean. Yeah. If next Boolean, then
you can grab the head of one list
okay.
and then recursively call a random.
Beautiful. Beautiful. Isn't that great? Okay. And so what's the concatenation operator here? Yeah. Hash colon. Yeah. And
And then call the function.
okay, actually, should I do that here, or wouldn't it be nicer to do what?
Put your else and wrap the whole if.
Yeah, exactly. Do the else here. This, and then what?
And then
Now you can
do your concatenate.
Yeah, do it here. We don't want that cruft getting in the way of our understanding. Okay, so what do we do here?
Call the function with the tails.
Call the function with the tails, right?
You left the bottom of the console a little bit up.
Sure, it's yeah. Let me see if I can resize it here. Okay. Okay. Is that better?
Yeah.
Okay. 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 The kiss of death. Okay. Let me just try this. Okay. So this is what it got. So what's wrong here? I forgot the 2. Okay. Okay. What do you think? What do you think? Good or not?
Good.
Okay. Okay. So how could I test this? Well, I could do val my stream equals random elements 2, and let's give it what? Stream dot from. Can't you do stream dot from?
Yeah.
One will be a stream from 0, so go 0, 1, 2, and the next, let's do it a stream from 100, right? Just we'll watch the first few elements of it. Okay, my stream, and how do we get the first couple elements? Take, sure, I'll take 20 of them, and then what? Force it. Okay, so it got the first 2 from 100, and then 2, 3, and then 108, and 6, 8, and we can tell visually it must be working because they're off by 100 sometimes, but it's basically going 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So, ladies and gentlemen, that's the stream. Sweet or not?
Semi-sweet? Bittersweet?
Hopefully not sweet and sour. Okay. Okay. Complete the sentence. Within an aspect-oriented program, the user gives what specifications that match whatever. At these points, action that the user has specified in what can be executed. What's the first one? What are you matching in aspect-oriented programming? You're matching underlying join points. And what is it that specifies which join points you want to match? Declarations of point cuts. And what do you what are you specifying the actions inside of advice? Okay.
Join points are where point cuts get put.
Yeah. Point cuts specify join points. The join points are in your program, whether or not you know about them. Point cuts specify which join points you care about, and advice specify what actions to take around those join points. Before, after, around. Yeah.
Sorry, what was the second point supposed to be?
Join points.
Join points. So
So what's the first one?
Point cuts.
point cuts. Point cuts. Point cuts specify join points, underlying join points, so that you can weave in actions specified in advice. Okay?
Specify point cuts to match join points.
Yeah. Yeah. What does it mean to curry a two-argument function?
Make two one-argument functions that stick together.
Okay, but let's sharpen that a little bit.
Translate a function with multiple arguments into a sequence of functions with one argument each.
Okay, so it stages the computation, right? Well, we'll have a method, let's say a function that has two arguments, and we turn it into a function that takes first the first element, then takes the second element, and then performs the original function with them. So it breaks up having to give them at once to giving them in a staged, staggered manner. So we give one little bit at a time, and we get back an increasingly specialized function that does this job with just a little bit more information with all the remembered things. And I actually asked you to perform a curry function via email, and let me ask you to do that now. I want to define a curry to operator that basically takes in a function and mumble. I'm trying to scroll over. There we are. So it takes in a binary function, a function that, sorry, that shouldn't say binary. That's a bit confusing. A function taking two arguments. That's an arity2 function. So this function takes two arguments and returns a value. The first of the arguments of the function type t, the second of type u, and function to return a value of type v. So function is something that takes a t and a u and it returns a v. And I want to define a curry operator that turns that, whatever function it passes is passed to it, it turns that into a curried version of that function. So tell me how to do that. Def curry 2. How do I do it?
Well, we need parameters, so it takes in a function.
Okay, so let's start typing those. It is true, parameters enough. So here's a function, and what's the type of this function? Okay. Well, okay, it takes two parameters, two arguments for it. The first of the argument is t, the second is u. So what do I type? Comma u, and then what is it? What does this function return?
Equals right arrow v.
Okay, yeah. Okay, but can I just specify this? What do I need to do still?
Letters in the name.
The letters, okay, so where do I put, what are these things? They are,
Type parameters.
yeah, type parameters. They're parameterized types, and where do I have to specify them?
In the name of the function.
Okay, TUV takes each of those, okay? And what's the return type of this function? Just to be clear about it, what does this function return? May help you think through what's going on here. What does it return?
Anonymous function with t,
Okay, so the function that's returned takes a what?
a t,
A t.
and then
It-
the end bracket.
And then that returns a function that takes in a u and returns a v.
Okay, this takes a u and returns a v.
Can't you specify currying just using two sets of brackets side by side?
For an arbitrary function?
I don't know.
No. It's a good question. You could certainly do it for particular instances, and we'll see that in just a moment. But okay, so ladies and gentlemen, this curry 2, it takes in a function that takes a tu and returns a v. And what it gives us back is a function that takes a t, and that, when given a t, it returns a what? function that takes u and returns v. So it does work. And so what is the definition here? What does it need to do its work?
Does it just return FNT? I don't actually know what those are.
So this thing needs to be something that takes a t. So how am I going to do that? So this was all the signature of this thing. What do I have to type here?
FN of T, I think.
Okay, so suppose I started to say this. What is it going to say? Where's the... So this is, again, just the type of this thing. So what is T going to be? If I said T, what would this mean? Yeah, it's going to be a parameter. What is T? T is a type. So we can't pass a type to a function. What do we need to do? We need to... So the return value of curry 2 is a what? It's a function. So we need to return a anonymous function. Good. What's that anonymous function going to take in? A what? Yell louder. Take in something of type T, okay, or we'll call it A of type T, okay, and then it needs to. We could call it a lowercase t, fine, and then given that, what does it return? Returns a function, and what does that function take in? Takes in a u. Give me a u. And given a u, what does it do? Sorry? It returns a v. And what v does it return? Computed by fn. So how do I get that v back? I've got my t, I've got my u. What do? Function is something that takes a t and a u. What do?
Give it T, little t.
I give it little t. Oh my gosh. Let me shrink this down. If your visibility is as bad as mine, okay. Oh boy, we're going to be in trouble now.
That's some brackets.
Okay, how many brackets? Anyway, I can't even see it anymore. I think it's one to end that one and one to end that one. Yeah. Okay. I think for a lot of practicing computer scientists, practicing software developers, we develop certain skills and probably certain parts of our brain develop in a unnaturally sort of developed sense. So I think one thing is the ability to read text that's scrolling really fast, and another thing is the ability to like count the number of brackets that we have open. Our descendants will think we have bizarre specializations, just like the ability to remember 10-digit phone numbers and regurgitate them upon need. Okay, so here's curry 2. So what do we got here? This looks like a big ugly thing. Let me make it slightly larger so that we can see it with less discombobulation. Here we go, ladies and gentlemen. So what do we got here? Well, the first part of this is just a signature. I didn't even have to include this, although frankly I think this statement, in a way, it boils it down to its essence of what the job of curry is. Curry takes a function, takes a t and a u and returns a v, and it gives you back a function that first takes a t, gives you back a function that then takes a u, and then returns a v. It's kind of, in a way, that boils it down to the essence of what it's doing. But the specifics of it are, it returns a function that, yes, takes a t. We have to name it t, lowercase t, and then takes a u. We have to name it lowercase u. And then whatever function does, we apply it to a t and a u. Right? Okay. So that's our curry 2. Now, Connor asked, could we we do this with multiple parameter lists? Could we somehow get it to,
So when you make a curried function, you can just say function name and then two sets of
when you
lines.
make a curried function, here though, we don't have a curried function. What do we have? We have a
Closure.
curry operator that operates on functions. So I'll see if I can draw this out a little bit more. This is a curry operator. I can apply it on a function of my choosing, right? So here we go. Let's try this. Curry 2, I'm going to apply it on a function whose job in life is to take string 1 and string 2. This is going to be a string, and this is going to be a string, and it's going to append them together. Okay? The 2. Thank you. Okay, so val curried concat. So I'm going to apply the curry2 operator to this function. What do I get back?
A function
Okay,
that takes a string and
good.
returns a function that takes a string and returns a string.
Okay, so this curried concat is a curried version of the string concatenation operator. Why? Because this is the string concatenation operator written there. It's a function performing it. And what I get back from curried 2 is something that takes the string 1 and then returns a function whose job in life is very specialized. Its job in life of the function, if I give it, if I have curried concat and I give it a first argument, foo, what do I get back?
Function that prepends food everything.
Foo, okay, so foo concat function, right? What sort of thing is it that I'm getting back? It's a function, right? And what's its job in life? If I give it bar, what do I get back? Foo bar. If I give it baz, what do I get back? If I give it foo, what do I get back? Okay, maybe this is seeming a little bit dull. But the point is that, ladies and gentlemen, this is a curry 2, this operator is a currying operator. You give it a function here, and it gives you back a function whose job in life is the same as the original one, but it's staggered computation. It's staged computation. It takes each element in turn. So this function that I got back, curried concat, basically will take the first argument, and that will create a specialized function whose job in life is to concatenate foo to things. And given that specialized function, I could give it bar, it'll give me foo bar. I could give it baz, it'll give me foo baz. This, ladies and gentlemen, is a curry2 curry operator. Job in life is to curry arity 2 functions. Now, per Connor's question and statement, if I wanted to define my curry concat manually, one way I could do that would be, how would I define it manually? My curried concat, how would I do it? I want to define a curried version of concat, how would I do it? This is, I think, what the string concat in 2 different ways. So how would I do it? What's one way to do it?
You would do it with def and just 2 sets of brackets.
Okay, I could, but that's the second way. I want to do it first in the long-handed way. How would I do it? Long-winded.
So what does that mean, long-handed way?
What I mean is I got to write it out in a way that will be longer, but more explicit and more sort of clear, probably for those less familiar with Scala syntax.
Same
So,
way we wrote out the other one, except instead of the
okay.
function, it would just be concatenation.
Okay, so we'll take in a string here, and then what do we get back?
Function that takes a string and
Return back a function that takes another string and does what with it?
concat string 1 and 2.
Concat string 1 and 2. Okay, so this is kind of
So you just define.
a very explicit way of doing it. It's a very long-handed way. It's not very crisp. There's a crisp way to which Connor alluded, and what would that be?
Def it.
Yeah, we'll just def it, ladies and gentlemen. Okay,
Notice that it
and what we'll do here is we will do this, and then what do we need? This, right? We need this, and what do we replace this with?
An equal sign.
An equal sign, and this is what we get. These, I would argue, well, except for the subtleties involved, the difference between a method and a function, these basically do the same thing. This one here, my curried concat 2. Why do we say it's curried?
Has two separate.
It is two separate argument lists, ladies and gentlemen, here. So we'll give it the first one, and it can give back to us a function that takes the second one, a partially applied function. So watch this. My curried concat 2 of foo, what is this going to give us back? Now, actually, we have to do something a little bit different because it's going to be unhappy. What do we have to do? We have to do this. That will give us back a function. That, ladies and gentlemen, gives us back a function whose job in life is to do what? Concatenate foo to things.
So the only syntactic difference is that you have to know it's a curried function when you call it.
You do have to know it's a curried function because it's only partially applied. That's right. You have to know it's a partially applied function. But I want to distinguish. This is for the very specific case of concatenation. What I created above was actually more general than that. It was actually a curry2 operator. Given any function here, it will give me back a curried version of that function. And I don't think one could readily improve that by using multiple parameter lists because we're getting a single argument in. Yes, Alex.
Can't you always tell if it's partially applied just by looking at the type of whatever the type is like?
Yeah, I mean, if you look at the definition of it, you could tell, yes, it would be partially applied because there's a missing parameter list here. There's a lot of functions in Scala that have multiple parameter lists. Some of them have what are called implicits taken, in which case they automatically can get the values from the context if it's available. Anyway, that's these two things here. Any questions on currying? Currying is a pretty big, pretty important sort of concept in functional languages. Yes, Tushita.
Other than staging, what are the advantages of currying?
Well, when we talk about staging is a profound thing in terms of its implications. Staging allows for partial evaluation. It allows for performing some of the computations when certain arguments are available earlier and saving the rest for when that information is available. So you can actually incrementally sort of do the job of the original function along the way with appropriate staging and currying. But it's more than that. It's more than that. Ladies and gentlemen, there are times where we write code to perform a job and we end up passing down information successively through chains of sort of calls and large numbers of different parameters. We actually saw some of this in the code we saw with Conway's Game of Life, even in Scala, and I didn't bother to sort of clean it up. But the idea here is that often we have information that we need sooner and other information that's going to take later. And what currying allows us to do is, instead of dragging around all this information that we've been accumulating along the way until the last little bit is available so we can actually do the job, we can actually pass around just one thing that accumulates more and more information inside of it. Because what's going on with currying, ladies and gentlemen, is something of great significance. What's going on within currying, and you can see it right here, is that a closure is being created. Ladies and gentlemen, a closure is being created. When I get string 1, what do I get back? What do I get back when I get string 1? I give back a what?
A closure of a function containing string 1.
A closure of a function that remembers string 1. And in general, instead of accumulating, dragging around all this information to be applied at the end, in traditional programming, maybe passing it down long chains of calls until you actually do the job way down there somewhere. What you can actually do is basically curry things so that the thing that you're passing along gets more and more information built into itself. It remembers it instead of you having to explicitly pass the arguments along. You're just passing along one thing that remembers a whole bunch of things. Because this function that I get back by curry concat, or the function that I would have gotten through so this function that I get back, that remembers foo. I don't have to remember foo anymore because it remembers it for me. So val, my concat. This my concat knows to do it with foo. I don't have to tell it anymore what it is. It just remembers to do it with respect to foo, and sometimes that's really valuable. We create special versions of functions that remember things when they get invoked by an event handler in our code. When someone clicks on something, it just does the right thing because it remembers all the information it needs to do its job. It remembers what string you're searching for, and so instead of saving away what string the person's searching for, it just saves and all the options on that. Are they searching for it in a way that's only uppercase, whole word only? You have a closure that remembers all that information, and when they say search for the next, it just knows how to do its job searching for all those things. We don't have to remember all these settings along the way because they're remembered within the function itself. I'm expressing it in a poor way. I'm expressing it in a way that's not completely clear. But the point is that creating closures, one of the main virtues of creating them is that they remember information. They store the information inside. They can store a heck of a lot of information inside necessary to do their job. And that frees us from needing to worry about that information anymore. We've given them the information they need to do their job. They're going to do their job when all the information is available. Meanwhile, they'll carry it away around so that we don't have to carry it in our shoulders anymore. That is a lot of the attraction of curried things. Okay? It's probably not the clearest way it can be put, but it's a lot of the reasons we use them. Okay, other questions about that? Questions? Okay, so back to the sample questions. 3 examples of monads in Scala. I uttered their names within this very session, within this room.
Option, try, and future.
Option, try, future. Beautiful. Give me another one. Stream. Sorry? Maybe it's I'd be tempted to give full credit for maybe, even though that's from Haskell. The same idea. It's not in Scala, but it's in Haskell.
Did we use maybe?
Could you use maybe?
No, didn't we use maybe in the REPL one time?
Maybe I defined maybe, but maybe I didn't. I don't know.
I thought it was in Scala.
I don't know. It's not in built-in thing in Scala. It's a good question, but it may be in Scala Z, which is kind of some neat extensions to Scala. But no, I'm not aware of it in Scala itself. We use option that functionally starts as maybe.
But there is on the slide.
Does it say maybe?
Yeah.
Where does it say
It
maybe?
didn't say,
Oh, well, yeah, that's not a Scala specific thing. That's my lecture on error handling in languages in general. So yeah, that's not Scala specific.
so how are streams a monad? What
Stream.
metadata information is stored?
So they're storing metadata on the objects. In particular, a lot of what they're storing is how to compute the next one.
Oh.
Yeah.
Because most of them don't exist.
Most of them don't exist at any one time. Yeah, only some of them exist that are already cached. Let me ask this, ladies and gentlemen. I didn't really emphasize this, but I felt I failed you in reflecting on it. I wish, when I reflected on this, what you probably wish to know is, did that neuron fire that I felt really bad having failed you about it at the time I was creating the exam or at the time I was creating the review materials? And that I can't tell you. But I feel I didn't tell you enough about something in Scala. It's a pretty neat thing. Here we go. Are you ready? Watch this. Okay, my array. Okay. Here we go. Okay. I should do a better job than that. Fine. It would be more interesting. So if I were really on the top of my game, I'd show you something pretty neat in terms of performance. So ladies and gentlemen, if I have this array, what can I do to turn this into a parallel data structure? Dot par. That will actually turn it into a parallel array. Now the significance of that is if I perform a map over that, what can happen?
Can compute them all at the same time.
It can compute, yeah, not quite all at the same time, but it'll break it up into chunks, each of which can be computed by a different core on my machine, for example. Okay? And again, if we had time to burn and so on, I could show you the performance implications of this and show you how if I had an array of 10 million, that actually I can eke out quite a lot of performance savings by mapping it out to different processors compared to just performing a serial map, doing it on one at a time. Instead, I break it up into pieces, and each of them performs within that one at a time within each of those pieces. But let me show you something else. Also a thing called view. Anyone remember what view is? I think I mentioned it in passing.
Lazy by name.
It's lazy by name. So distinguish between the two broad types of laziness we see in Scala.
Cached and non-cached.
Okay, good. And give me other words we use to describe those.
Name and need.
Name and need. So laziness. So laziness by name and by need. Distinguish those in terms of the implications for performance and for memory, or for functionality. What's the distinction between them?
Need is cache requiring
Good.
memory.
So need is caches it. Once it computes it, it caches it. Give me something that's laziness by need in Scala.
Streams.
Streams. Once you start evaluating those elements of the stream, they're remembered.
I thought you just said by name is cache.
No, by name is actually recomputed each time we ask for it.
The view is by name. We haven't gone over the
View is by name, not by need. View is by. So need, cached. When we need it, it performs it and it remembers it. Takes memory after that, but it doesn't have to recompute it. By name, every time we ask for it, it recomputes it, but it doesn't have to store it, use memory for it. Streams are where between these? We heard it earlier, but it's
By need.
by need. Streams are here. Suppose we use a lazy keyword. What is that? By need as well. I'll show you that in a second. Suppose we how if we have a parameter that's given this is almost a giveaway, a call by name parameter.
Probably by need. That makes the most sense.
So call by name parameter is by name. How do we write that in Scala?
Add the equals arrow kind of thing before it.
Yeah. We'll see that in a second. What else is here? Views on a data structure. Now, having done a view on a data structure, we can then perform subsequent operations on that data structure. So we could, for example, map it, right? We could go through and we could, for example, take double and we could, square it here. And this is not going to be quite as interesting a case because of the original array that we're dealing with. But fundamentally, we end up having a lazy structure without remembering each element along the way. Let's take this example, though, of laziness. So suppose I say lazy val. Well, here, let's do this. How would I know? Ladies and gentlemen, if you don't remember this, tell me how you determine which it is. Like if you were sitting in front of a REPL, how would you determine which of these is by name? Let's suppose I wanted to know for a lazy variable or value whether it was need a name. How could I figure that out?
Calculate the first couple and then try to get them again.
Okay.
If they're still there.
Okay, how would I know if it's still there? Because here it's referring, let's say, just to one value. Like,
if you force the first 10,
okay.
and if it was by need, it would remember those 10.
Okay, but a lazy value is often just used for some expression. Long computation of 35 or 24. Yeah, you could potentially do that, but there's an easier trick, ladies and gentlemen.
If there's some kind of logging that's stated in a method you call.
Yeah. So Janelle, I think is on top of it as normal. So def. So my function. Okay. My reporting function. How's that? So it's going to take in a double, and it's going to return back. By the way, suppose it didn't return a value. What would I put here instead of equals?
Not an equal.
You don't do that. Okay, so this is going to do print ln of x, and it's going to return x. Okay, so this is going to be a very simple function. But here I'm going to do this val, a lazy val, my val. Okay, and it's going to be my reporting function of 3.14. Okay, there we go. So you notice it says lazy. What does that mean?
You have to do it.
Yeah. Okay, so suppose I said my val. What will happen, do you think?
It's going to print it out. and then
Okay, prints it out. Now, suppose I did it again. If it is by name, what should I see?
Another 3.14 print.
Yeah. If it's not by name,
Just the result.
just the result. So is this by name or by need? This is by need. It's actually cached the value. Otherwise, every time I used it, it would say that. If I wanted to create a by name parameter, how would I do it? Well, so I could have my function, so lazy by name. And what would this look like?
arrows and then the type.
Yeah, double, right? Something like this. And I'll just return back. So lazy by name. I'll just here I'll do lazy by name plus lazy by name. Okay, here we go. Okay, there's my infamous function. Okay, and ladies and gentlemen, if I pass it now, this thing, my reporting fn 3.14, what's going to happen?
Print it twice.
Yeah, why twice?
It's recomputed.
Yeah, this is a by name parameter. It's lazy, ladies and gentlemen. Until it's needed, it won't compute it. That's significant, because if it doesn't need it, it won't compute it. Give me an example of something I said was a powerful way to extend the language, because why can this be used to extend a language to new constructs?
You get infinite streams or infinite constructs.
Yeah, and yes, and this is non-strict. So for example, I could implement an if, a special type of ternary if function or something like that. Depending on the first value, it'll evaluate the first argument and the second argument and the third argument or the fourth argument. Otherwise, it doesn't evaluate them. And that allows me to sort of extend the language in the sense that it's like implementing an if statement, which you can't do in Java in a nice way. Here, ladies and gentlemen, this is call by name, so I can pass it something that evaluates it each time. It evaluates it, it uses it, and it doesn't cache it. Okay, laziness, ladies and gentlemen, laziness. Okay, 3 examples of monads. Yes, these are monads. Okay. For those of you, there are probably few grad students in the room, but I'll be teaching a course next year, as I did last semester, which talked about a lot of the implications of these monads, or a fair bit of it is about the implications of these monads for large-scale data science. Large-scale processing. And one of the real advantages of streams, and in fact, lazy views for large-scale data processing, is they use a minimum of memory. Why do they use a minimum of memory? If I'm performing a long pipeline of computation, say, performing successive transformations of data on a stream, why do I say that doesn't need to take much memory? Yeah, you don't need intermediate collections, because it's by demand, right? Lazy things are by demand. They're not computed until they're needed. And it's not until that first element is needed that it's computed, and then it performs all the operations along the way to get the value. It's maybe not needed till way down that pipeline, and when it's needed, it'll perform each operation successfully along the way and get that value back. Yeah. So what? Every summer I run boot camps here. Run boot camp. People come from around the world, and I use sound effects. I use side effects as well, but I use sound effects to illustrate things, and it catches their attention. I tell them only Canadian computers make that sound, so you miss out on it elsewhere in the world. Anyway, if Canadian computers freeze up, they're people can excuse us because it's cold. Anyway, sorry. Yes.
So if you create a lazy view,
Yes.
is that the same as a stream?
There's one important difference, and that's why lazy views are down here, are up here, and streams are down here. What's different about a lazy view compared to a stream? A lazy view is by name, and therefore it does not use memory along the way by remembering each value it computed. And that's significant.
Wait, so so what's the point of declaring something to be lazy at the beginning?
To have something like this, you mean like a lazy value?
Yeah.
A lazy value It could be a computation that you only want to occur very selectively under certain cases it should be performed. So you declare it a lazy thing, and when it gets computed, it gets remembered, but otherwise it doesn't have to be performed. So it's only performed on demand, which can be quite efficient. But that's different from the memory advantages I'm talking about in the context of large-scale data processing. This is kind of a convenience to have lazy variables. It's lazy values. It's quite useful, but it's not required.
So the same kind of lazy, can't you do it on views and it's almost
Yeah.
like a stream?
Yeah, it's like a stream. Yeah, in a way, it's like a stream, but streams have special support in terms of that syntax we saw, pound, colon, and stuff like that, and you can. I think maybe you can destructure them more easily. They just have some more built-in support, but you can do a lazy view, which gets you much of the same benefit I'm talking about for large-scale data processing. Because the key thing is, ladies and gentlemen, with large-scale data, tens of millions, hundreds of millions, billions of elements, you don't have the luxury of loading it all into memory. You load it into memory, game over in terms of performance. Your memory fills up, your system, comes to a halt. You're not going to be able to perform things effectively. So this ability to perform the computation incrementally on an element-by-element basis, performing longitudinally each series of operations for that element in turn, without the need to ever bring into memory the full collection, that is huge. Because you never have to bring in those billion elements. You're performing, and you don't have to go from a billion element collection to a billion element collection to a billion element collection, allocating and deallocating along the way. Instead, you're performing the operation with each element in turn, maybe discarding it at some point, maybe aggregating it, perform it for the next, aggregate that, etc. And in that way, you basically avoid loading them all into memory. And that's what systems like Spark can allow us to do and map them out to large numbers of machines. Okay, other questions?
Are views testable?
Testable?
Tomorrow.
You should know about their existence.
Okay.
I'm not gonna ask you to create a view and apply and engage in frauding behavior on it. But you should know that they exist, and you should know that they're by need. So they cache their value. I'm sorry. I was thinking lazy things here. Views are by name. Yeah. By name. In contrast to streams, which are by name. And that's an important difference, because you're right. There are two ways of getting data structures, collections, which are lazy. But one is by need, one is by name. And that's important in terms of options for processing. We don't always want to carry around the memoized values, the values that are remembered from earlier processing, like we do with streams. Sometimes views gives us what we need. Okay, so with a lazy view, with this sort of lazy view here, we can get back and perform this. And notice it hasn't yet performed the computation until we need it here. It knows how to perform the computation, but because this is lazy, it hasn't yet done it. We could filter out those that are greater than, 3.0, greater than 3.0, etc. And then we could sum them up. I don't know. Yes, there we go. And when does it perform all this? When does it perform this map of each element? It performs it when it needs it. And what drives it to need it? The sum, and so it's going to get the filters of things, and for that it's going to perform each of these operations, etc. Okay, suppose you have a monad of type M with type parameter A, supporting map, filter, reduce, and flat map. Using Scala's type notation, so just the notation for types in Scala, please specify the type of argument passed to each of these methods. What does map need? What does map take? Map takes a function, and what's the type of the function passed to map? So suppose I have a monad, and it might be a stream, it might be an option, it might be a try. So here I have my monad, and this is M, of some type parameter A. And I want to consider, suppose I have one of these nice monads, one of them good monads, and I want to call map on it. What do I give it? What's the argument? It maps what to what? It's a function, and it maps what to what?
A to M of A. Or A to a monad.
A to
Collection.
A to B to a collection of B's.
Okay. Yeah, it can map an A to a B, type A to a B, and what does it return back? I didn't ask for that, but what does it return back? MB. So this map could do toString on the element of that, right? On a string, for example. Yeah. Okay. How about flat map? This is the most important distinction I'm draw out here. Okay, what does flat map take? So the thing that we pass into flat map takes an A. Good. And then what does it return? Now that's the rub. This is the key thing. And you're going to want to know this. What does it return? What is this function passed into flat map give us back?
If you have a container flat map with A's, then it goes from A to a container of B.
Good.
And it
So
returns a container.
I like what I'm hearing. So remember, one way to think about it, I think it's not a bad one. This is from Functional Programming in Scala book. What they say is, you use map, think about map, you use it for cases where maybe you have something that could be success or failure. And if it's a success, you want to map that successful value to some other value that's known to be successful. Use flat map if the operation that you're giving it might itself fail. So you want to be able to return back something like a try or what have you within this method. So it actually maps each A to an M of B. And then what's the return type of that?
But then that M doesn't have to be the same as the M on the top, right?
The same M, different type parameter. It does. So in other words, if it's a try and you apply flat map, this can't return an option, for example. It can only do a try. Yeah.
If it was a stream, you could return not.
I don't think so. Let's try it. Give me a second. My hypothesis is that it's this. Okay. So you'll notice that this is one that you have extra flexibility. You can get back on it. So let's give it a try. There's no use speculating about it. So let's have a stream. Val my stream 2 equals stream from 0. Okay. And we are going to do my stream 2 dot flat map. And maybe Alan's right. That would be really cool if you could do it. So it's going to take in a value, and it's going to do, let's just do sum of this, okay? Yeah, okay. Okay, now that's interesting. Mumble. Do you see what I see? What do I... That isn't what I expected to see. I expected to see something different, but... Is that what you expected to see?
Kind of, yeah.
Well, what
Yeah,
what
so...
does flat map do? There's no second layer to bring out.
Well, basically what flat map was doing here is with doing basically this of sum of n. And so basically what it's done is it's collapsed down the it's collapsed down the options into their actual values.
Oh, that's what you said, flat net.
Some of it is. It's just that normally we think of this as operating on like an array of arrays or a stream of streams or something like that. But it's interesting that here it operates. So you wonder what happens if suppose we did none.
If we give it an array of
What?
some
Oh my gosh! Oh my gosh!
What?
Ladies and gentlemen, we could wait till the cows come home, and we'd still be waiting.
Oh, it's trying to take all the nuns.
Yeah.
It's trying to take the first 5 nuns
So-
out of none of the nuns.
It erases none this one.
So, ladies and gentlemen, I declare this session, not the review session, but the Scala session, defunct. Okay, kill it. Okay, and now I will restart it. Okay, so yes, it is. It's mapping it down in a kind of interesting way. Let's try this just a little bit more. So val my stream 1 or my my stream 1 anymore. Okay, stream dot from 0, and then let's my stream 1 dot flat map, and let's do this. Yes, okay. So this makes a lot of sense. Sure. So yes, Ellen is correct, but actually this. So this is some other. This could be an monad n. But the interesting thing is, watch this. If we did n of int here, and we did array of n. N minus 1 and n plus 1. Oh my gosh.
What? Did your Scala thing that you supposedly killed finally crash?
I think when you killed the job, it did the job.
Yeah, so I don't dispute the possibility. Okay. So here we've actually we've collapsed it down into one level. So this could, Alan's correct, this could be actually a different monad, but what we do get out is the original monad flattened down accordingly. So that stream has incorporated the results of the map.
Yeah, I've tried it with the sequences and arrays and
Yep.
vectors,
Yep.
and it just disregards the n that are there. And
Yeah, it just sucks them down into the original thing here. But it does allow these. Okay, and meanwhile, filter. What would that take? What is the? These are all higher order what? Functions. What does it mean to be a higher order function? That's an actionable question. Takes in functions as arguments, or returns a function, or both. Yeah. So filter, what does that take?
Takes in a function that
A
Returns
returns a boolean.
a Boolean. Good.
And returns the monad of A.
it's not the monad of A, it would be A.
Actually, it returns a monad
A
of
stream of them, you just get a smaller stream of them.
of a strip of smaller. Yeah. So you have a stream. It goes to a subset of stream. You have an option. It still returns an option. This is a big difference from null for the Tushita question earlier, right? If we had val O1 equals this is an option of int, and we basically do none, then we can still say filter, this thing greater than 3, and what are we going to get out? None. Ladies and gentlemen, this is very significant because let's suppose that I had this. This was the example I probably should have shown Tushita earlier. Here,
Are you
watch.
just gonna add more things to the filter after?
No, well, watch this. Vector of. Let's import scala.util.random and everything in there. Okay, val my array one dot. Okay, dot array dot fill, and I think here you take this and then you take next double, right? Here's an array of a bunch of doubles, right? How many doubles? 100 of them. Now watch this. Watch this. My array one dot map so I'm going to take each of those doubles and I'm going to cube it, and I'm going to filter to find those that are greater than 0.99.
Done this in class.
Sorry?
You've done this before.
Yeah. What do you think I'll get out?
Not many.
It's 1, right? Suppose I were to be even more strict. How many do I get out? None, right? Now, what's the issue here? Well, suppose I want to do a sum on these. Okay, yeah. So that's actually that's interesting. It has a sum of 0 in this case. Suppose I wanted to do a further reduce on them. What does reduce take as arguments?
2 elements.
2 elements. So double 1. Call it x and y. Double. Okay, and then I'll do x plus y. What do you think? Okay, so what happened here? What's going on? What do you see at the root of the?
It's not a reduce option.
Exactly. So this here is having difficulty because fundamentally we're not able to take an empty thing and basically reduce it appropriately. Okay. Yes.
Will reduce crash on just one element? Just interpret the other one as 0.
That's a good question. I think it'll just take that one argument. Yeah. But the point is that if we were to have this be a reduce in a way that allowed for an option, that could actually allow a value to be produced that's actually not in fact it doesn't throw an exception, rather it indicates it as a none value, and then the processing could continue. There could be further processing associated with it. So I don't remember if there's, yes, here we are. There we go. To reduce option, and so then I could map that to its yeah, sure, 1 over it. So 1.0 divided by this thing or something like that, and I'd get back a none. Whereas if I just did reduce, what would I get back?
With exceptions.
Map is not okay. I'm not a value of double in the first place. Yes, so I wouldn't actually be able to do it with this map here anyway. I'd be doing 1 over it, but in any case, it would exception out. So this is a way of sort of stringing together computations that's robust to issues that can occur in the midst of them. Okay, whereas a null that could be produced along the way could cause an exception, and an empty value or an exception that's thrown along the way can cause problems. Okay, please distinguish between an operator and a function in Java 8.
Oh, we forgot to do the reduce.
Oh, reduce. Yeah, thanks. Okay, so what's reduce? What does reduce take? Two things. An A. Okay. Something like that, I think. So, actually, this thing you have to pass to reduce. Yes, in our case, we always did it with two A's. It actually doesn't need to do that.
But shouldn't B be also the A because you're taking the items from the same?
No, this is actually, it's starting with an A, and it is, okay, yeah, so there is an issue here. I may be confusing it with fold here. Fold, you can actually do this sort of thing, but fundamentally, the idea is for one of them, and I can't remember which, you actually can return a different value. So you could take, for example, these, here, let's try it here. So, so my stream, try this, my array 1 dot reduce, here we go. And suppose instead of doing this, so let's just do it with this. This is A, and then what returned? A, right? A is double, right? Here we go. There we go. But imagine if we went like this, dot toString plus that guy, okay, dot toString. Yeah, so now it would, okay, let's see if we can do this. Yeah, no, it's not going to. But fold, there's fold left and fold right, and I think it may be fold right that allows you to do this, where you basically can end up having it return a different value. So I think toShoot is right in this case. For reduce, we have this guy here. And certainly that's the most common case. But there are versions of this, and I think it's with fold or one of the other operators. Where, yes, it's reduced left and right. And some of those allow you to actually accumulate values that are of different types than the one that you're accumulating. And basically what you provide, I think, is an accumulator that combines, the values in the monad with the values being accumulated to return a value being accumulated, then maybe something that treats how to treat the initial value of it. But in any case, that's reduce here. Okay, great.
For reduce there,
Yeah.
is the return value of monadic A? Like, is it a monad as well, or is it an A?
Reduce gives you back a monad of A here. Yeah. Because if you apply it, to a, let's try this. Should be careful here about that. So if I apply reduce to a, so here's O1. I'll do val O2 equals sum of 3. And if I do O2 dot, I'm not even sure, yes, it is reduced, okay. You notice, by the way, per the Tushita comments, this is all the same here. So if I were to do, A of int, comma B of int, and I were to do goes to A plus B here, it's going to give me back that, right? So it's giving me back, yes, a monad. If I were to do it with a stream, yep.
Didn't it give back an integer? Because
Oh, yes, right. No, you did right. It gave back an integer. Sorry, I was toning out. This is a monad. This is an integer here. Yes. So it is giving back an integer. Yeah. So I take that back. It's an A. it's an A. So it's reducing it to an A. Yeah, yeah, that makes sense. Okay, so so Java 8 support for higher order functions. How to distinguish an operator from a function? What does an operator do compared to a function?
Forms of transformation on the same type.
Yeah, so basically an operator, it may take other types, but basically its return value is going to be the same as its first argument. Okay. It may take additional ones, but its first argument is the same return type as its last. Compared to a function which can take in arguments of different sorts and return yet a different type of value. Okay. Creating code in Scala. Okay, this is an important one. This is an important one. Val versus var. Val, var.
Immutable versus mutable.
What is mutable and what is immutable? This is the key question.
The reference of a val is immutable.
Okay, is the thing referred to mutable?
Yes, it can be.
Can be. So fundamentally, the way I think about it, and it's not particularly privileged, but val and var both define names. Okay, val. I don't like having to name these V and W. We just go U and V. I don't know. In any case, var and V. What is the name V referring to? What's the meaning of V? What is it? What is it? What is the quantity named by V?
Some sort of value.
It's a value, ladies and gentlemen. What is the quantity named by W?
A box that holds a value.
A box that holds a value. It's a location that holds a value. Those are very different things. Now, of course, we can write W plus 1 or W plus W or whatever, W times 2. And if there it's referring to the value in that location. But fundamentally, the var refers to a location. A var refers to a location. A val refers to a value. What is held in a location? So W refers to a location. What's in that location? A value. So W refers to some location that holds a value. There's a value in that. Maybe it's a reference to something. V is referring to a value itself. It's not referring to a location. Because this refers to a location, a box, the var, it can be updated over time. Now, the thing I want to really, so are people okay with that notion?
So like if we put an array in the value, it doesn't, what does that mean?
Okay, so a value can be of several different sorts. A value can be a reference. It could be including a null reference. It might be, in some languages, there's this distinction between primitive and non-primitive, and actually even in Scala there's a difference between sort of ref values and not. But fundamentally here, a value could refer to an array over here. Because it's a val, does that tell us anything about what, if it refers to something, whether or not that thing is mutable or not?
No.
Could it refer to a mutable thing?
Yeah.
You bet it can. It just refers to the same mutable thing over time. This is referring to the same mutable thing over time. I don't change who my mother is over time, but my mother changes over time. My mother is always the same person, but but she's changing over time. It's the same array that this val can refer to. That array could evolve over time. Sometimes it will refer to something that's immutable, that doesn't change over time. A vector doesn't change over time. A map doesn't change over time compared to a mutable map. An immutable map doesn't change over time. Default map doesn't change over time. So just because something's a val doesn't mean it refers to something that's always immutable, but it refers to the same thing. Once you refer to it, it's referring to that thing. You can't then say it refers to nothing. No, it refers to that array. Just that array may change in size. The elements of it, actually the size doesn't change, but the elements can change. An array buffer can change in size. Okay. A var, meanwhile, could that point to something? Could a var? So a var refers to a location, and that location might refer to some objects, right? Could refer to them, and they could change over time. Could the objects referred to by the location associated with a variable? Could those objects be immutable?
Yeah.
They could be immutable. The difference between a var and a val is that which objects are referred to by the var changes over time, right? A var, this location could refer over time to different things. So, sorry?
I think we got it.
Yeah, I'm having to be cautious in my other family examples of things that can change over time. Today is notable for being my wife's birthday, and I don't want to give other analogies within the family which can change over time, but mumble. So who's I don't know, who's the oldest student in my lab can change over time, right? Okay, that lacks convincing power, but the point is that over time, some things can change. What's my home can change over time. I can change my home in Saskatoon. I could move from one home to the other, that could change over time, and fundamentally that would be similar to what a variable is. Over time, which thing is referred to by that variable will change. With a val, the thing that's referred to by it, which thing is referred to by it doesn't change. The thing referred to by it, the thing that's actually referred to by it, it's the same thing, over time that it's being referred to, the contents of that thing may evolve. God, I dodged that bullet. Okay. Please indicate a major consequence of calling .par and then performing operations. Well, it's parallelized, and so these operations can be performed in parallel.
Does it slow it down if you say have under 100 or something?
Yeah, there's some performance overhead for sort of a minimum size at which it makes sense, because there is some data structures required for parallelization, synchronization, or what have you.
You wouldn't have to know that, like, ballpark, would you?
No, I don't. I think if you look at the examples that are done, I think in the ranges of tens of thousands or something, it could start to be beneficial, I think. Yeah. And these days, in our databases, you might have tens of millions commonly in a given database, and so you can easily imagine it being quite useful. And certainly there's many, with billions out there. Okay, given a method, contrast the difference between setting advice to work based on an execution point cut and a call point cut for a method. So you could say, interrupt this, the execution associated with method foo or call of method foo. What's the difference? I actually have a slide about that that's quite clear, but what's the difference?
Inside or outside?
Inside or outside? Which is outside?
Call.
Call. Call will capture just before the call to method and just after the call is returned. The activation record for foo is no longer on the stack. It's no longer inside of foo. It's outside of foo, either before it's called it or after it's returned. By contrast, execution actually captures it within the call to foo. It captures it within that call in a way that allows it to actually capture the values within foo, or the context within foo. Okay, good. Yeah, option is useful. Well, I did that already. The point is that basically it allows us to eliminate a lot of cruft associated with special casing, either around exceptions or around nulls, that otherwise encumber our code, make it less clean, less clear, more error prone, and less concise, certainly. So those are reasons. To find a curried version of a string concatenate, we did this already, and we did that already. I think we finished those example questions. What other things could I answer?
Why was this one so different than what you posted?
Oh.
The one on the website and the one on the email.
Oh, okay. Well, I'm all ears. Let's go. Maybe I accidentally skipped some here. Let's go take a look.
The one on explain why handling exceptions compose, what problems the handling exceptions compose when writing code.
Yeah. So I must have somehow been going through it too.
This jumps all around the middle.
Yeah. Okay. Here we go. True, false. If we have an object referred to as a val by a val in Scala, that object cannot change. False. Please give an example of a method as defined automatically by a case class in Scala. Apply, unapply, in the companion objects, and apply, in fact, in and also methods for accessors and so on. True, false. Scala, declaring class A as a case class automatically creates an underlying class A and a companion object A. True. Please contrast the implications of two different uses of call by name. Okay. Okay. So if you have a call by name parameter and you mention it twice, what happens? It gets evaluated twice. Twice it's evaluated, run, and so it's evaluated twice. How about declared using the lazy keyword? It's all only by need, only evaluated once. Give a plausible practical example where call by name could save execution time. Good.
A database with 10 million elements, you only need element 10.
Sorry?
Your database with 10 million elements, you only need element 10. You only need to do computations up to element 10 or something.
Right.
That's good for all lazinesses.
I'd have to unpack that. But that's interesting. But this issue with logging is key. Why is it helpful for logging? What happens with logging?
Side effects.
No, okay, side effects can happen with logging. That's not so good because we like to turn logging off sometimes. What else goes on with logging? This is
So,
actually pretty important.
If you have so much logging, sorry, like taking up memory space, you have to swap stuff out to this.
Okay, but with logging, one of the real things we like to be able to do is to log more or log less, to throttle the logging. We like to turn it off sometimes if we don't need it, or turn it on at full throttle for debugging. We might only want to log high-level things, might only want to log low-level things. And here's the deal. With low-level things, we might be calling the log things a lot with things that are, when we perform turning them into strings, reporting on all these low-level features of our code, it actually takes a fair bit of time to sort of get together that information to log. So in the log message, we're actually printing out various things and so on that just to call a log requires a certain amount of computation. You know, we're reporting the number of items in the dictionary. And that's part of the log message. This many items are in the dictionary. So in the log message, when we call log, we're actually saying log, you know, dict.size or something like that, eh? And it gets logged. Now, if we perform that without call by name, what happens? If we perform it in a traditional way, and let's suppose that's the most detailed type of logging of informational messages. What happens if we don't care about informational messages?
Still computes it because it's done strictly.
It's done strictly, it's done eagerly. So in order to pass the value to the log message, it has to call dict.size, perform the size calculation in the dictionary, and pass it along to the log message. And then what does the log do? You know, concatenate it with the string, all that sort of stuff. And then what does log do? It says, oh, I'm not logging informational messages right now, throw it away. Throw it away. It might do that 10,000 times a second. I don't need to log this. Thanks for computing it. I don't need to log it. Thanks for doing all the work. I don't need to log this. I don't need to log that. That can actually take a fair bit of performance cost. Exact a fair bit of performance. Why is call by name any different?
It's lazy.
It's lazy. And so what does that mean in concrete terms?
It's turned off, it won't compute it.
Yeah, if it's turned off, it says, oh, this is a logging message at a level I'm not currently logging. It won't even evaluate it. Do you see the point? It will never actually compute that dict.size because it's not needed. It won't compute the summary statistics on the contents of the current database. It won't perform the checks on the integrity of a data structure for the logging. So not logging informational stuff, I don't even have to evaluate this. And so it never actually performs even the concatenation of the string. It never even performs. String, this thing is of this size or whatever. It never performs that unless it's needed. So logging is a great example of something where we can actually save a lot of time. There are others as well. And I'm perfectly open to the idea that one also described might be useful. Okay, give an example of a higher order function in Scala. Sorry? Map. Filter, reduce, flat map. Please explain problems handling exceptions could pose when writing code in the pipeline style. What happens when an exception goes off?
Kind of kicks out of the current context, so it'll break the pipeline.
Yeah, it breaks the pipeline. How can you restart it? It kind of bombed out halfway through. How do you get back to that point in the pipeline? And it makes it very difficult to write those sort of nice logical sort of compositions. Indicate a consequence for memory for having a pipeline operating a lazy collection versus a non-lazy? Well, the consequence is you don't have to load the billion elements into memory. Each of the billion elements can be computed all the way along the pipeline and then just progressively combined in with the results of others. And you don't have to ever bring in the full billion elements into memory at once and then create the next billion as a result of the map, etc. Okay. And we talked about null. Define a curried value, curried version of concatenate. We did that. Curry 2. Did I miss some still?
Yes.
Which ones did I miss?
Like the second page, it starts with
Yeah.
suppose that there's a class B that is declared.
Oh, good. Yeah, great. Thank you. Suppose there's a class B that's declared as a subclass of type class A, which is not in fact a proper behavioral subtype. Worry about general scenario where how a bug could be introduced in such a situation. Okay. What I was looking for there was the situation. All you know, if you have code which is operating on A's, all you know is that this is an A. You're counting on some features of A-ness, on the properties of being an A. And you're counting on those in your code in ways that might be pretty profound. This never changes over time. This thing is always guaranteed to match this property, what have you. And if someone gives you a B and you think it's an A, and it violates this property, somewhere else in the code knows it's a B, but you don't know it's a B. All you know it's an A. That B can then violate your assumptions, because Liskov substitution principle basically defines behavioral subtype. If B is the subtype of A, that means that B observes the guaranteed properties of A. And so if B does not observe them, that code that's processing it as an A, is counting on it having the properties of an A, could be broken by a B. Okay, that's the idea. Yeah.
If a question is phrased like this, do we assume that when you're writing class B, you don't have access to the code for class A?
No, you could. So, first of all, in general, as software engineers, we shouldn't assume we always have access to the code. But even if you had access to the code,
I just mean for answering the question. Should we just if it doesn't specify? Should we
I would
just
say
take away
I would state your assumption
Okay.
with respect to that. But more than that, even if we did have access to that code for A, does that help?
No, it just means it currently works.
No, it just means it currently works. It may not work in the future. That's a lot of the issue. Okay. So given a class A, give an example of sort of information be needed to be specified in an inheritance specification. Versus those seeking to use instances. Well, we talked about it earlier. What calls what things have to be overridden together. Okay. True, false. Consider a class C that's a subset of another class A. In general, C having a specification that accords with the spec is not enough to ensure that C is a safe subclass of class A. That's true. It can be a safe subtype as defined by Liskov substitution principle. But in terms of subclassing, there's other needs, like the fact that it may be counting on the implementation of A in terms of what calls what. And that's not going to be specified in the Liskov substitution, in the specifications reasoned about in the Liskov substitution principle. That's a function of the implementation of A that may change over time. So just because it accords with the Liskov substitution rule in terms of the promises made by C compared to those of A, doesn't mean that it's going to be safe as A evolves over time. 2 or fewer sentences indicate what it means for a language to be lazy. Well, can anyone tell me?
Specials are evaluated when they're needed.
Okay, that's a common, and I'd accept that as an answer. I'd accept that as an answer. One thing is that it means that programs can be non-strict, so we can pass a function, something that doesn't complete as a computation. That doesn't necessarily mean, so it never finishes as a computation. That doesn't mean if we pass that function, that function call will never return. Maybe it ignores that thing passed to it, for example. So, we pass a log message, something which never would finish, but we're not logging at that level, and so it just throws it out. Describe the basic notion of an aspect. It's almost like I mixed together the solution and the question now. Describe the basic notion of an aspect. Cross-cutting concerns within a program. I think the latter part was meant to be a solution to the first. Ladies and gentlemen, we have these codes, and they have concerns which cut across the different kind of components of the program, the classes, the functions. There's things that come up. They're used, they're implemented, they're performed in many areas of a program. They're thematically grouped. They're all about a certain thing: logging, transaction management, security, tracing, database access and persistence access, etc. But they're located they're scattered in many places in our code. And where they're scattered matters. I mean, they're not located at random points in the code. They're located at certain places that are distinguished by certain features. And these aspects are not well captured by traditional programming language constructs in procedural and object-oriented fashions. And even in functional contexts, for many years, they haven't been captured well. So an aspect basically allows us to name, put in rules to place, and achieve a separation of concerns by separately specifying in a centralized place these locations and these places where things get woven in. Okay? That's what I see aspects as being most critically about. Okay? And that achieves separation of concerns, a sort of consolidation of that logic in one place, a generality. As we extend our program, it can be automatically woven into new places. It allows that logic for performing the logging or the persistence, the transaction management, or the tracing or whatever to be evolved over time, because it's all concentrated in one place rather than having to go update your code in 100 different places just because your logging infrastructure has changed. Okay. True, false. There's many things we can do with closures that are not possible with object-based abstraction. Not true. We might be able to do it more cleanly, more crisply, more transparently, more beautifully, or more elegantly with closures. But we can do it with objects. Look, basically, you can think of, crudely speaking, you could think of an aspect as an object of sorts that wraps together certain information that it needs to do its job, with some description of what it's supposed to do, when called. with the things passed to it. And that's quite similar to things we can do with objects. And in fact, in the Java implementation of Conway's Game of Life, we did that. We created objects that basically, whether anonymous classes or named classes, that basically whose job in life was to apply some rules. The rule to perform the classic Conway's Game of Life, or to allow cells to survive if they have between 2 and 4 neighbors alive, that sort of stuff. We did that with objects, and we can do it. It just, often it's more cumbersome and more clunky, etc. But we can do it. Virtually all these languages are Turing complete. I mean, whatever you can do in one, you can do in the other. The question is how ugly does it get? That's a lot of the question. How poorly performing does it get? True or false? It requires less work and care to build a mutable object out of an immutable places than it is to, requires less work and care to build a mutable object out of immutable pieces. Build a mutable object out of immutable pieces that don't change, than it is to build an immutable object out of mutable pieces. Which of those requires more effort? Building an immutable object out of mutable things, or a mutable object out of immutable things? Sorry?
Immutable out of mutable requires more work.
Immutable out of mutable requires more work. Why is that?
Because there's a danger with composing it out of mutable pieces, and you want to make sure that it doesn't get changed once.
Yeah, it doesn't get changed out from under you. How do you prevent it from getting changed out from under you? If your data structure is composed out of these things, what do you have to be careful about? Give me some concrete examples. They were in the video.
You don't want to give out references.
You don't want to give out references to them. Good.
You create new kind of versions every time you do.
Okay, good. Yeah, so if you want to pass out some information, rather than passing out a reference to your internal date, you create a copy of it. What else do you have to watch out for?
Constructor, where you pass
Yeah,
the values.
things coming in, right? Like in a constructor. A reference to an external thing, you can't just say, oh, I'll use that for my internal date, because that could be changed by someone from outside. So you have to make a copy of that. Building a mutable object out of immutable pieces, not a big deal. Okay, those individual pieces within them, you're not going to be able to change things. You may have to, sometimes allocate a new one and get rid of the old one or something like that. But it's not a big deal. It's not a big headache because these things can't change. And in fact, these immutable pieces, what's the defining thing about an immutable piece? You can reuse it. You can share it, right? If you have a big num, and here you have this big number, right? Here's my big num, b, and then I take minus b. All I have to do is have it refer to something that says minus of this big number. I can share the same underlying data structure because this is not going to change. I can reuse a lot of pieces of it. Reuse a heck of a lot of that original data structure. Even if they have to create a new, because I want to add one to the size of a vector, create a new one, it can still use the pieces of the old vector which are immutable. Make a case as to why aspects can aid the transparency and clarity of code. Well, I mentioned it earlier. It takes a lot of scattered stuff, puts it in one place, captures the rules for its placement, why it's located in different places, and succinctly states those rules and allows you to separate that out without having to look at it at the original place. But in tools like Eclipse, you can see where it's woven in, so you can easily get there if you want to see it. Okay? Okay, are there other questions I've missed? Other questions that I've missed?
Did you mention the Java 8 operator versus function just when I was over the
Yeah, I did. It must have been where you're at, but yeah, basically operators. The operative distinction here is that an operator will take in and return the same type of item. Now, it may take in additional things as well, but an operator, for example, an operator of an int operator, will take in ints and return ints, okay? Now, it may also take in an int double, but it returns an int. And so it's kind of defined as having a type that it takes in and type that it returns that are the same. And that cuts down on how much you have to specify in the type parameters. A function, by contrast, can take in and return very different types of things. So it might be like the one we saw. It takes in a t, then it takes in a u, and then it returns a v. Okay? Other questions? Yes?
Just making sure, filter guarantees order, right? So if you filter.
Correct.
Yeah.
Correct. Correct. Now, one thing I didn't talk about is there's something called filter with. It's pretty nifty. And basically what filter with does, it actually doesn't even filter down, it doesn't create a new data structure. What it does is it creates references to the old data structure of which elements were filtered correctly. So it actually can save memory and avoid needing to sort of create a subset of the original data structure. Rather, it just refers to which are the elements that were selected. And that actually ends up playing a role in monads sometimes, particularly with the for construct. Do you know about for? Sorry? Well, okay, so the for construct in Scala, it's awesome. Awesome. Okay? It allows you to do things like this. And I've got to be cautious about what I try to do here. Oh man, I should have imported Scala.io. Okay, let me import that. Scala.io import. What is it? Scala.util.io? Yeah? Yeah. No. Scala.io. Okay. Oops. Dot this. Okay. Okay. So now I should be able to do, watch this, val v read int. Read int. Hey, what am I doing? Sorry, folks, it's getting late. Okay, so I just did read int and I typed something on the keyboard, and I did something invalid there. Typed something invalid. I'm going to type something valid now. 234, and it gives me 234. Okay? Now watch this. Right. Okay. I think that should be correct. Banking on my memory. Okay. Okay. Try. Oh man. What is it? Scala.util. Oh god. Okay. Okay. Yeah. Okay, fine. Yes. What's that? Dot try. Yeah. I think this will import all of it. I'll here. We'll end it. Let's try this. Try of 1. Happy. Okay. And I'll just double check my memory. Yes. Okay. Good. Happy. Okay. Here we go. A try of read int to option, yeah, B, try of readint to option. So here are two things, and then I'll do, and then yield A divided by B. Okay, so I'm gonna enter here 4 and 0, and oh no, okay, oh man, beautiful thing. Okay, so why isn't this caught by the try? It should be doing it in terms of the try. That's the thing. Okay. Oh well. So A, let's try this. B, and Z is A divided by B. Okay, and then we'll yield Z. Okay, I think it's gonna still happen. Yes, map is not a member. Mumble. Okay, sorry folks. I actually have a nice example of it in the slides. If any of you want to see it, it's in the it's in here in the lecture slides here, and it's in, I think it's in the monads area. The basic deal is that this notation allows us to, I was trying something a bit too ambitious, but it allows us to take these and perform operations on them successively in a way that's kind of minimal syntax, and allows us to just, here we go. So C goes to A plus B, and then yields no, it should be, I should have done yield A plus B instead. This is going to give trouble. Yeah, okay. Okay, sorry. This is what doing it from memory takes. Okay, there we go. And we yield A plus B. It should be fine, I think. So basically, this is performing operations on, yes, there we go. So here it's actually performing operations on the underlying objects as if they were just the values, when really they're options of these values. So we can perform whole sequences of operations on these values using this for notation in a way that basically strips away the need to write actually map and flat map and filter, etc. And that's something which Scala and actually Haskell also provide with this sort of for notation. And I think I have some examples of this in this monad chapter that I didn't end up getting to present for you. No. Oh well. So I guess that's too much. That's certainly not on the exam. But fundamentally, for comprehensions, these sort of for operations, they allow us to very easily define operations over collections of monads that are very, very clean. And we just describe the operations as if we're operating on the things inside of the monads, and it will actually end up performing them on the monads themselves. Okay? Okay, those are all the prepared remarks. Other things people would like to ask? Going once?
Is this class in danger of getting curved down?
Sorry?
Is this class in danger of getting curved down?
I don't think so. I don't think so from what I've seen of the marks thus far. I guess it depends a little bit on what happens with the final exam, but based on my comments here, I think people in the room are probably going to do pretty well on the exam, if memory serves you over the next day. So I think I've anticipated a lot of things of the exam. You're right that the take-home exercises people did pretty well on because they're 1 or 0, right? And if you struggled with them, you could do pretty well reliably. But some people didn't. I know that. some people ended up not attending to them, and that ended up sacrificing some potential marks. So,
Perfect.
yeah.
So that means, what's the format for final?
So I thought I made comments about that earlier. So when you say format,
For mark, I mean.
oh, the full marks on
Yeah,
it?
for marks.
So you're saying what fraction of the class? 30%. Yeah.
32.
What is it? 32%.
Depends on
Thank
what
you.
option you take. It's around 30 though.
Yeah.
It's to be decided.
I think the reference here is, I think it's right around 30, with maybe it's a little bit different with people who are pursuing projects compared to pursuing the assignment focus. But yeah, it's around 30% of the marks. And I don't have much option on that. I mean, fundamentally what it comes down to is from the U of S, there's stipulations for how much finals, the minimum final can take. A final exam in a class like this is 30%. So I just have to hew to that standard. But I think we've prepared pretty well.
Do you think we're gonna be able to finish the exam tomorrow? Because this seemed long to me, and then you said the exam's longer than this.
The exam is longer.
Wow.
So that's a very good question. It's well within the limits of what I've seen in the past. I think it's a fair question, but I think it's well within the limits of where I've seen students readily complete it and some leave early in the past. However, and I say this advisedly, I do think you're going to want to pace yourself through it. I think you're going to want to refer to the time, and you're going to want to move yourself along and make sure you're not being bogged down in questions. But honestly, I can't imagine any question taking too long because it is so complex that you're just thrashing on it. I think it's going to be pretty clear. Do you know how to proceed with it or not? And I don't think it's a lot of complicated code you're going to be writing out, with the possible exception of the last question. So go take a look at the last question. Go look at that early.
You said you all want to have a 2 additional discussion.
Sorry?
The post email said that we want to have a further discussion for 2 questions. We didn't do that. Oh, we did that?
Yeah,
We
they
did-
were
yeah.
Korean.
Oh, yeah.
Yeah, the curry. Maybe it makes you hungry for dinner. Okay, what other questions? Other questions? Nothing? Okay. So I will look forward to seeing you tomorrow. And I'll be with you all through the exam. Please ask questions if any come up during the exam. The exam is closed book, no computers in the exam.
I have a question for
Yeah. Yeah, sure. Give me